can define, with these two pictures, you can define two regions. In one, in which, so below this point, roughly, in which the elastic energy loss is more than the inelastic energy loss. So here, the Sn dominates. And there will be the other region on the other side, where the electronic energy loss is much larger than the nuclear energy loss, and this is Se dominant. Then this is subdivided into three parts. One is the maximum, the other one is below maximum, the other one is above maximum, and just let us forget about this region of interest, which we have to talk about later. So the region 1, and just let us forget about this region. When the velocity is then the velocity level and the velocity level and the velocity level and the velocity projectile velocity projectile velocity what is the correction, what is the improvement in the calculation of nuclear and electronic energy losses. And this is an example, gold in quartz, where the nuclear and electronic energy losses are calculated with the help of software stream. And now it is not logarithmic scale, so the curves, they look a little different. And this blue one is for the total energy loss. Now, if you do the reciprocity analysis, there will be corrections. The electronic energy loss at lower energies, it will become less compared to that calculated from stream. So this correction will be there, so that the total energy loss also it becomes lower. There are further tweaks. One is unitary convolution approximation at low velocities given by G. Sievert and Grande. And so I don't want to tell the details of this, but this is implemented in another program, which is CASP, which also can be found from the link which is here, and I will share the slides. And this info is also given by Professor Sulema. Another tweak is the consideration of synergy of nuclear and electronic energy losses together. And this is a very good work by Professor Sulema and collaborators in physical review in 2011. And here you can see the details of how nuclear and electronic energy losses, they are synergistic. Experimental work on the damage profile and ion distribution of swift heavy ions in compounds. For this particular case, you can look at this particular reference. Once again, this is provided by Professor Suleiman. And this, the first of the references, of the 4 references which I gave in the beginning, this one is highly useful reference for the experimentalists. They can get answer to any of the questions they face while analyzing or interpreting their data. Now, there is variation of nuclear energy loss and electronic energy loss with this. So basically, the picture is that if you have sufficiently high energy ions coming inside a material, with this picture or this picture, there will be loss in energy because of the elastic and inelastic collisions. The ion will keep on losing first, mostly the electronic energy loss or dominance, so electrons are moving away. When it comes very far, very deep inside, most of the energy is lost. So the nuclear energy loss is dominant now, and then all of a sudden, all the energy is lost and the ion gets implanted inside. So like you can have this picture where you have a film and substrate, you can have multi-layer and substrate. Then now suppose you consider this picture. Suppose you have 2 identical projectiles of the same energy passing through a material medium. So one of the ions may have scattering 1, 2, 3, 4, 5 number of times. And when it comes out in this process of multiple scattering, it will lose some energy, delta E1. There might be a case that another identical projectile, it will undergo little less number of scattering. So it will lose little less amount of energy. So if you see the energies of the particles which are coming out, the projectiles which are now coming out, if the material is thin enough, then the outgoing particles will have various energies. And these energies will be like E plus minus delta E. So they will be centered around some energy E with delta E width. And this is called energy straggling. The difference in energy of the particle. Now, if you increase the thickness, there might be a scattering, the particles may still come out and you have the energy straggling. But if the thickness is too large, then because of the energy lost, one of the projectiles may get implanted somewhere here. The another which is scattered more, it may get implanted much earlier. The one which is scattered less may get implanted later. And then the implantation itself will take place at different places, centered around R by an amount delta R. This is called range straggling. So these are the things which will happen. Then there are collision cascades. So if there is an ion entering the surface, it may hit one of the atoms which recoils in this direction. This is scattered. So there will be recoils and secondary recoils and tertiary recoils. All these kinds of recoils may take place if the ion energy is high. If the recoil energy of this is high, then it will recoil another. If the recoil energy is still higher, it will recoil another. So there will be a series of collisions. This is called collision cascade. And if this event becomes very dense, the collision becomes very dense, collision cascade, then it is also called thermal spike, because at any particular instant, all the atoms inside this particular volume, they are moving because of the collision. So it's like having kinetic energy, which is equivalent to some temperature. So the temperature of this particular region will be high. This is called thermal. So I think I will stop the first part of the lecture here. And so maybe now Indra can guide me.
So, Ambut sir?
If any question is there, I think maybe you can address.
Okay.
From the
Sir,
chat box.
there are few questions written in the chat box. So, maybe we can request Manoj Kumar Rajbhar to unmute his mic and ask the question to Sanjeev sir. Manoj Kumar.
So I can see the question here.
Okay, sir. So, shall I read it for you?
I will read it.
Okay.
Can we calculate the electronic energy loss by Bethe block if our ion energy is below or nearly equal to 100 keV? Certainly, yes. If we cannot calculate it by Bethe block, then what is the accurate theory to calculate it? So as such, Bethe block, as I told, it calculates the energy it calculates the electronic energy loss for all the energy range starting from zero, so it can be done. As far as the accurate theory is concerned, I talked about some of the corrections like the reciprocity analysis. So these are the corrections which once again they are valid for everything. We still can calculate by Bethe block and have the correction. Is it okay?
Yeah, Manoj, is it okay? Or you want to ask further questions? Okay, any other participant? Any other question or query to sir?
Yeah. Yeah. I'm going to try for the rest of it.
So if not, let us thanks Sanjeev sir. So we cannot clap, but I am thanking you. So we will break for maybe 10
Thank you.
minutes to soothe your throat, sir. Please have some
Yes.
water or, and then we will be joining in 10 minutes.
Sure, sure.
Okay, thank you, sir. Ashokan sir, you
So
want
12
to
sessions.
mention something?
Indra, you just
Yes,
said
sir.
people should not log out. Otherwise, they will be again asking for permission to log in. So they should just uh, uh, have their mics and this cameras off and wait for 10 minutes and not log out. If people log out, then everybody will have to be let in again.
Okay, so you have heard him already, Ambut sir. So please do not log out of the school virtual platform. So we'll be meeting in 10 minutes. So soothe yourself, have some water. Sanjeev sir will be waiting for you after 10 minutes.
Yeah, yeah.
Okay,
And
thank you.
you can show me the tea on the screen so that I can take.
Tea, okay, I'll find out one picture of tea.
Okay. So I'll come back at 12:15.
Okay, sir.
Sanjeev, I think you can start.
Okay.
Mm.
So, is it visible and am I audible? Hello? Hello? Dr. Ashokan, am I audible?
Yeah. Yes, your voice is
Okay, so,
okay.
and the
Maybe
slides
can
are
you?
coming.
Yeah, maybe you can slightly reduce the volume, little bit,
Okay,
not too much.
okay, okay,
Yeah,
okay.
yeah.
I'll try to speak little less loudly because I'm not getting where to do this. So I hope it is okay.
Yeah, it's okay. It's
Okay.
okay.
So this is part two, illustrative applications, mostly on Swift Heavy Apps. Actually, on essentially on Swift Heavy Apps,
Yeah, you can make full screen.
full screen. So before I go to Swift Heavy Ion method interaction examples, only one kind of comment on low energy ions. With low energy ions, you can do ion implantation and beam mixing and so on. And for example, in the ion beam mixing, you have a thin film deposited over a substrate, and ions of the low energy ions they irradiate the material, and at the interface there could be elastic collisions and there could be cascade of collisions. There could be recoil implantation, and because of that there could be a rearrangement of atoms, and atoms of one species may mingle with the other, and you can have a mixed region, and this you call ion beam mix. So this is just to give an example. When it is high energy ions, what we have seen is that when the ions they are moving inside the material, they are just creating disturbance in the electron system. They are not able to give recoil to the atoms inside the material. So with the high energy of the Swift heavy ion, the only achievable effect is heating of the electron subsystem. So the electrons they get a lot of energy, they get a lot of kinetic energy which is equivalent to temperature, so it's equivalent to heating the electron subsystem, but no atomic movement is anticipated. However, there are reports that Swift ions can produce deformations, and first of such reports was in 1982 in insulators. Some other observations are modifications in metallic classes, amorphous metals, crystalline metals. And this is a summary of what happens. On the y-axis, it is the electronic energy loss, and on the x-axis, it is like the distance inside the material. When the electronic energy loss is very small, there could be modification of the materials in blobs. If the electronic energy is high, then the blobs can elongate. When the electronic energy loss is even higher, they can start getting connected, they become cylindrical, and when it is quite high, there could be a continuous track of modified material of width up to 10 nanometer or so. I will show you some of the experimental results, and these slides are provided by Professor Suleiman. So this is a set of pictures, TEM pictures of tracks or the modified material in Y3Fe5O12. Now what you can see is that when the electronic energy loss is 8 keV per nanometer, you can see that there are small blobs of the modified material which are visible. And these can be represented with this picture here. When the electronic energy loss becomes around 12 keV per nanometer, you can see connected extended regions, which can be represented by this picture. And when the energy loss is 25 keV per nanometer, it becomes a continuous modified cylinder with a radius of 3.3 nanometer or so. And other references are provided here. You can plot the radius of the modified material, which we call track, ion track, with respect to the electronic energy loss. So you can see that as the electronic energy loss increases, the effective radius of the modified cylinder it increases. And once again, so the same references which are presented here. Now, on the same material, what they have done is they have tried to put the irradiated samples inside chemical agents, and they were able to etch out the material and do the transmission electron microscopy. And you can see the morphologies, and once again, it even after the etching, the holes which are created, they also have the same kind of morphology longitudinally. There are further references which are given here. In another material presented in this physical review B paper, Bi2SR2CaCa2OX, you can see the morphology, longitudinal morphology once again by cross-sectional TEM. And this is a picture which is a schematic where it is shown that when the electronic energy loss is low, then you have isolated kind of spheres of blobs of modified material which start getting elongated, they start getting joined, and then you increase the electronic energy loss, they become continuous. And the radius increases if the energy loss is higher. This is another set of pictures for track radii in GD2 TI2ZR2-X47. This is radial morphology, once again by TEM, which is presented in this paper. Some other references here. So you can see the track from top. In one example, it is amorphous inside the track, the modified material is amorphous when it is GD2 TI207. If you put little bit of zirconium in this, then you get a core shell kind of structure where core is amorphous and shell is crystalline. And if you replace Ti with Zr completely, then the modified material is completely crystalline. And you can see the diffraction patterns, electron diffraction patterns, which are the speckles. So this is another example. There are a few other examples of the microscopy, transmission electron microscopy of tracks. One of the examples is the one which is presented earlier, Y3Fe5O12. From this particular reference, this is the track seen from top for ZRSI04 at the surface orientation 111. So you can see once again the modified material or the track in calcium fluoride. You can see tracks, small tracks, not this big one. So longitudinally, so this is perhaps a cross section. You can see the tracks. Then in silicon tracks are there, and so this is the reference. Then for gallium nitride, you get the tracks. For nickel zirconium, you get the tracks. For graphite, you get the tracks. So there are modified materials by Swift heavy ion irradiation. Swift heavy ion irradiation modifies the material. This is another set. Once again provided, all these slides are provided by Professor Pulema. He requested me to present here so that he focuses on some other issues. So once again, track radii, and they are increasing. So in GD2Ti207 with different ions, and for each ion, so electronic energy loss increases in this direction, and the track is amorphous. In a picture, you can find out what is the amorphous fraction. The amorphous fraction, you can see it is increasing with increasing electronic energy loss d by dx, and you can plot it, and you can get kind of an exponential increase in the amorphous fraction. You can do indirect observation of these tracks by Rutherford backscattering, crystalline Rutherford backscattering, which is crystalline near surface, wide angle X-ray scattering for polycrystalline materials, mass power spectrometry for magnetic materials, swelling measurements for bulk measurements, bulk materials, UV or infrared absorption. This is limited by wavelength, electrical conductivity, Raman spectroscopy. There are various other way of indirect observation of the track. So take the example of this CRPS, crystalline RPS. So this is once again Y3Fe5O12, where 4 MeV per nucleon lead has been used. And if you increase the number of ions which are irradiating the surface of this Y3Fe5O12, which is measured in terms of the fluence, so the ion fluence, and you calculate from the Rutherford backscattering spectra the disordered fraction. So there is a mistake here, Ti, disordered fraction, then you can see that it goes like this. This is another result which is obtained from X-ray diffraction, and amorphous fraction is calculated, is plotted with respect to fluence. It also goes up and then saturates like this. And you can fit all these data of the modified material like disordered fraction and all with some statistical law, y equal to y max 1 minus e raised to the power minus sigma phi t, where sigma is the cross section of the ion track. So if you fit, for example, this curve, phi is the fluence, t is the time, if you know, then by fitting you get sigma, that is equal to pi r square, and from there you can get the radius of the modified material or the track. Another example of indirect observation of track in Y3Fe5O12 once again. So you have the mass power spectroscopy here. Before irradiation, the spectrum is quite sharp, you can see qualitatively, and this corresponds to ferromagnetic component of iron inside this Y3Fe5O12. And after irradiation, there is a change here in the middle, and you can see a doublet here. Earlier, it is a combination of the well-known sextates, 1, 2, 3, 4, 5, 6. So you can see there are 2 sextates here. Now you can see that these sextates, they have been converted to doublets, and these doublets, they tell that the material now the spin structure is now paramagnetic instead of ferromagnetic, and from here you can calculate the paramagnetic fraction. And so the paramagnetic fraction, if you calculate and plot it with respect to the fluence, then once again you get a curve which goes like this, which can be fitted once again by 1 minus e raised to the power minus sigma phi t. And if you plot the cross section of the track, not with the fluence, but with respect to the electronic energy loss, then you can see that it is increasing linearly, of course, but there is some particular electronic energy loss below which there will be no deformation, no kind of track formation inside the material. So there is a threshold for track formation. In this case of Y3Fe5O12, where lead 15 MeV per nucleon is used, the threshold is 7 keV per nanometer. And the measurements on the same material with some other technique, the crystalline RBS, they also give the same results. So in this case, the cross section is linear with SP. And from here, there was a guess that the cross section is equal to pi r square, where r is the track parameter. So from here, you can plot the track radius, r is the track radius with energy loss. So certainly it will be a parabola. And the same picture, if you add, so you calculate radius r now with three techniques, indirect techniques, paramagnetic from the Mossbauer, CRBS, and TEM images. You can see that more or less they follow the same pattern. So once again, you can say that the sigma, which is the fitting parameter here, this is equal to the pi r square, where r is the track radius. And then you define, so from here you define sensitivity of the material towards swift heavy ion. So for example, this Y3Fe5O12 can be modified by a swift heavy ion if the electronic energy loss is more than this. But there might be materials where there is no deformation at all, whatever be the electronic energy loss. So the ones which can be modified, they are called sensitive, swift heavy ion sensitive, or She sensitive, or SHI sensitive. And those which just cannot be modified, they are called swift heavy ion insensitive. And in these references, basically, you can find out some work on which the sensitivity of the materials is being talked about. For example, in this case, there is a mixing between nickel and titanium, but nickel is not sensitive. And so these are the references where you can see what are the results in the case of multi-layers and how they are interpreted in terms of sensitivity of these different kinds of materials. I'm not going into the details of finding out what are the sensitivities at this point of time. So once again, I come back to the schematic of this picture, where there is modified material by swift heavy ion. But the question is, how is it possible? Because the swift heavy ions, they are not supposed to dislodge atoms by giving recoil energy to the atoms during elastic collision, because there are no elastic collisions. So what is the mechanism for the deformation of the material, which requires the atoms to be displaced from their place? And the only way out is that the energy which is transferred to the electron system by the ions, that has to be once again transferred to the lattice or the atom. Then only the atoms will move from their side, and then they will modify the material. Now, in order to understand this, there are two ways of thoughts, two streams of thought, or two models. These are essentially two models which are being discussed. There are more which are not very relevant in these days. So two streams of thought. One of them is the Coulomb spike or the Coulomb explosion model, and the other one is the thermal spike model. What is the Coulomb spike model, Coulomb explosion model? You have your material, you have an ion coming along this path. The ion has a positive charge. It deposits energy into the electron. So as soon as it enters, the electrons of the atoms in the vicinity of the ion path, they get energy from the ion. And because of that, these electrons may get excited and they may get dislodged from the atoms, and these atoms may become positive charged. And this may happen throughout the path of the ion. So you temporarily create a cylinder of ionized path. Now, what it will lead to? It will lead to the buildup of an electric field, which is radial in direction. So because of the radial symmetry, cylindrical symmetry of this, there will be electric field which is radially outwards. And this electric field, at what distance, what is the value of this electric field? This is plotted here by some calculations, by some theory. So if TR is the characteristic lifetime of the ejected electron, which is equal to 10⁻⁻16 to 10⁻⁻15 seconds. You see, the electrons are ejected, for example, from this atom, but then since this is an ion, this will recapture the electrons in the vicinity. So there will be a recombination of the electrons, and this becomes neutral. So, but there will be a time TR of the order of 10⁻⁻16 to 10⁻⁻15 seconds when all these atoms will be ionized. And the electric field, for example, for Z1 equal to 92, it will be maximum somewhere here at this distance. For lighter target, for Z1 equal to 92, the heavier target, this is the picture 4. There will be large amount of radial electric field at around this distance, which may be somewhere here, which will be created. And because of this large radial electric field, there will be a Coulomb repulsion between these ions. And so this is the Coulomb repulsion. The Coulomb repulsion will start from the atoms on the surface, then it will keep on going. Because of the Coulomb repulsion, the atoms will move radially outwards, but after that, there will be recombination, these will be neutralized, and because of the elasticity, they will come back to their position, but they may not come back to their own crystalline position. And as the ion goes inside, the process happens for each layer of the atoms, and ultimately what you can see is that within a cylinder of some particular radius, the atoms are disorganized. They are not in the crystalline place, and so there is homorphization. So this is one kind of proposition how material modification can take place because of the Coulomb explosion in the form of cylindrical ion tracks. And this is a good reference which talks about the theory of this Coulomb explosion. What thermal spike model, on the other hand, says is that once the ion is passing through, it is giving a lot of energy to the electrons in the vicinity. The electrons get kinetic energy, and which is equivalent to temperature. So the electron subsystem, which is represented by gray background, this becomes red, which is hot. So the electron subsystem becomes hot, and the energy which is being given by the ion to the electrons in the immediate vicinity, it is diffused outwards radially, and it is shared by the electron subsystem also away from the ion path. And this heat diffusion is characterized by the heat diffusion equation, where E represents the electronic component, T is the specific heat, so T is the temperature, T is the electronic temperature. There will be a change in the electronic temperature, dynamic change in the electronic temperature with time. That will be decided by the gradient of the thermal conductivity, electronic thermal conductivity multiplied by gradient of. So there will be del dot here, gradient of the temperature, which is instantly there. And then it will have the source term, how much the ion deposits the energy. This is ART, this is the deposited energy. This depends on the electronic energy. Once this happens, this heat will further diffuse into the lattice subsystem by introduction of a coupling mechanism here. So there is a complete coupling constant G. This is called electron phonon coupling. So the heat will be added by the ion, and it will be subtracted by the diffusion of heat into the lattice subsystem. And the lattice subsystem now is heated up slowly with the similar kind of equation, where there is no source term now because the ion doesn't provide heat to the lattice subsystem, but the heat comes from it. And that way, so that way the lattice subsystem gets heat and it gets heated, and in certain circumstances it can get molten, which is represented by the red dots, not at the crystallite position. So this is the thermal spike model. This is a calculation of the temperature of the lattice. So I am not able to move my okay. So what has been done here is that these set of two partial differential equations is solved numerically for the case of 230 MeV gold in iron, and the lattice temperature, that is this T, capital T, is plotted with respect to time by with the parameter how much distance, at what distance you are from the ion path. So if you are just at the ion path, this is the curve representing the lattice temperature versus time. If you are at 1 nanometer away from the ion path, you will have this curve, and so on. Now what we can see from here is that there is a melting temperature. There is the melting temperature of the lattice, that is the iron lattice here. We can see that the material within the radius of about 3.5 or 4 nanometers, it acquires temperature which is more than the melting temperature. So the material in the vicinity of the iron in a radius of about 3.5 of about 5 nanometer or so, it gets molten. So this is the thermal spike model, which predicts the melting of the material inside the medium. There are finer corrections to these calculations, which perhaps will be discussed by Professor Thulan. Now this is the time scale. So the passage of the ion starts here, and this side is the Coulomb spike model, and this side is the thermal spike model. According to the Coulomb spike model, there will be ionization of the medium in about 10⁻⁻17 seconds or so, and then there will be Coulomb explosion in a time range of 10⁻⁻14 to 10⁻⁻13 seconds. And because of the Coulomb explosion, the material in a cylindrical zone will get modified, and you will get a modified track of about 1 to 100 nanometers. In the thermal spike model, on the other hand, this is the part 2. So in a time scale of femtosecond to picosecond, there will be transfer of the energy of the ion to the electrons. There will be sharing of the energy transferred to the electron subsystem in the electron subsystem itself, and there will be an increase in the electronic temperature. So this is the time scale for the rise in the electronic temperature. Then in the range of 10⁻⁻12 to 10⁻⁻10 seconds, this energy is now transferred to the lattice subsystem, and the lattice may get molten within a radius of 1 to 100 nanometers. And if you see this picture, once it is molten, it becomes cool at a very sharp rate. You can see that the rate of cooling is about 10⁻14 Kelvin per second. So this is equivalent to quenching. So whatever is the modified material, it is frozen. So you get a modified track or the latent track of 1 to 100 nanometers. Now the problem with the Coulomb explosion model is with metals. In metals, the charge and electron recombination may take place in this time scale, which is much before the Coulomb explosion could take place. So although there will be ionization, but there will be recombination, the ions are gone, and there cannot be Coulomb explosion. So this Coulomb spike or Coulomb explosion model is not valid basically for metals. While thermal spike model, it can explain everything in metals, insulators, semiconductors, everywhere. This is another picture provided by now Professor Suleiman, where there is another set of time scales which are more of practical considerations. So once again, you can see that within 10⁻⁻17 to 10⁻⁻15 seconds, there is the energy deposition from the ions to the electrons. Then, so the energy is deposited by the ion to the electron. Then, in 10⁻⁻15 to 10⁻⁻14 seconds or so, there is plasma formation. Means the energy given to the electrons is diffused out and is shared by other electrons in the vicinity. Then, in this time scale, 10⁻⁻14 to 10⁻⁻11 seconds, this energy which is there in now the electron subsystem, this gets transferred or diffused to the lattice subsystem, where you can have boiling, where you can have melting, and then there is quenching, and for the quenching you have the modified material, which is latent track. And the way with which you can see experimentally these phenomena is that you have to have experimental techniques which work on the equivalent time scales. For example, if you want to see the energy deposition on electrons, you have to do in situ experiments with the very fast in situ experiments which can look at the phenomena which happen at such fast rate. For the plasma formation, when the energy is transferred into diffused into the electron subsystem, their Auger spectrometry. So here it is very difficult and it is not achieved so far. But here you can see from Auger spectrometry, for example, which has the time scales of this kind, you can see the evolution of the electron temperature with time. There is another technique, sputtering of atoms, by which happens in this roughly time scale. And here you can watch the energy transfer which takes place from the electron subsystem to the lattice subsystem. Then you can have latent track formation, which can be seen by PEM images because these are frozen. Now you have very large time scale. You can use imaging techniques in order to see the latent track, and you can use chemistry which takes place even at higher time scale to etch out the tracks and see the tracks. So these are various techniques which can be employed in order to see the phenomena which are happening at different time scales and which are proposed according to the thermal spike model. There is one consideration apart from this, apart from what we have studied, the thermal spike model and the Coulomb spike model. This is the velocity effect. What is this? Let us see this picture once again, which came in the beginning. We talk about swift heavy ions, that is the one which have the electronic energy loss dominant, and we are somewhere here. And we have seen that in this region, the velocity of the ion is equivalent to the Bohr velocity. In this region, so here the velocity is less than the Bohr velocity, and here the velocity is more than the Bohr velocity. Now, you can have an ion with two different energies, one here and one here, but both have two different velocities. And you can see what is the effect of the velocity of the ions in swift heavy ion matter interaction. And out some theory for why or what kind of velocity effect you could expect, but there are experiments. So one of the experiments, so some of the experiments will be presented here. So these are the references, and this curve is for from one reference for material GD2 Ti2O7. You calculate the track radius with respect to the electronic energy loss. You have seen that the radius is sort of linear or parabolic. Now you take two ions with the same electronic energy loss, for example here, 20. One with lower energy, that is lower velocity, lower velocity, and the other one is with higher velocity. You can see there is a difference between the radii of the track which are generated on the interaction and the radius generated by the ion with higher velocity. This becomes lower compared to the lower velocity ion. This is the velocity effect which has been observed in various experiments. And how I can interpret this is that if you have very highly energetic ions which have the velocities more than the Bohr velocity, so they don't have sufficient time to interact with the electrons in the atom. They are much faster than the velocity of the electrons in the atom itself. So they will have less time of interaction and less amount of energy will be deposited in the electronic system, then less amount of energy will be transferred. So this is one kind of interpretation why there is velocity effect. And this is another example in calcium fluoride. Once again, you have two kinds of ions, and you can see once again that the track radius is less for the higher velocity ion. Now I would like to discuss whether swift heavy ions can produce mixing as well. You know that ions, if it is Coulomb explosion, for example, all the explosions or all the atomic movements are radially outwards. Even the heat dissipation according to the thermal spike model is radially outwards. And suppose you have a thin film deposited onto a substrate, and if you wish that there is a mixing, what you need is longitudinal motion of the atoms in order to have the mixing, while the forces, the effects, they are all transverse. So can there be mixing? Yes, it can be. So if you see, according to the Coulomb spike model, the ion goes from one kind of dielectric medium to another kind of dielectric medium. The electric fields, they are different in one medium than in the other medium. This gives rise to a break in cylindrical symmetry, and then there could be radial, the transverse components, not the radial, the longitudinal components, and because of the longitudinal components of the electric fields, there could be motion of the atoms on one side towards the other side, and there could be a mix. So Coulomb spike model predicts some kind of mixing across the interface. Similar thing happens with Swift heavy ions concept. So if you have an interface between two kinds of materials, and then there is electronic energy deposition, sharing of the electronic energy in the electron subsystem. So in one material medium, there will be more of the cylinder which is heated. The electrons in more of the radius, they may get heated, and in the other, they may get heated in the less diameter of cylinder. Then when the transfer of electronic energy via the electron-proton coupling happens to the atoms, then the atoms, now you can see they become red or pink. So there will be one kind of modified radius on the top, and there will be melting in the middle. There could be another kind of modified radius below, beyond the interface, but still there could be melting in the vicinity of the ion path. So there is a molten material above the interface, there is molten material below the interface. So for a very transient time, about picosecond or so, they will stay in the liquid state. And if there are two liquids, they can interdiffuse. And because of interdiffusion, the atoms from this side may go from this side, and atoms from this side can go to this side, and there could be a mixing. So this mixing is most probably due to interdiffusion during transient molten state. So we tried to do one experiment in order to verify that it is really because of the thermal spike mechanism. So we took one iron thin film deposited onto silicon and bombarded with 230 MeV gold ions, and we did something called elastic recoil detection analysis to see what is happening at the interface. I will not tell the details of what is written here, but this is a part of the elastic recoil detection analysis spectrum. The other part from here onwards, it has not come. But what you can do is this spectrum can be converted into a depth profile where on the y-axis you have the fraction of iron atoms with respect to depth. This can be reduced from the ERDA spectrum. What you can see is that when the ion fluence is very low, or as if you have not irradiated the iron silicon interface, then there is full iron up to this distance and full silicon from here onward. Since we cannot have zero fluence, if we have zero fluence, the curve will become very sharp here. We have some finite fluence. So for finite fluence, we have this picture. If you increase the fluence, this becomes more slopy. If you increase the fluence further, it becomes even more slopy and even more slopy. So what does it mean? For example, if you consider this blue curve, then already a lot of iron atoms which were there earlier within this depth, they are not there anymore. They have gone into the silicon side. Similarly, silicon must have come on this side. So this is called, these profiles are called depth profiles. You take one of the depth profiles and do something called metano analysis, and you can find out what is the diffusion coefficient of iron in silicon and what is the diffusion coefficient of silicon in iron. So these are the curves which are the calculated interdiffusion coefficients in the unit of 10⁻⁹ meters square per second. And on the x-axis, it is iron atomic fraction. So this comes from Metano analysis, and these different curves are for different fluencies. What we can see is that all these curves, they asymptotically meet at this zero, x equal to 0, that is silicon, because iron is 0%, so this is mostly silicon, so iron in silicon. So everything, it goes to one point, and this point will represent the diffusion coefficient of iron impurities in mostly silicon. Similarly, on this side, all the curves, they reach to one point, which is D2, which represents the diffusion coefficient of silicon in mostly iron. And these two values from this curve, they come to be of the order of 10⁻⁹ meters square per second. And the literature values for liquid state diffusion, they are also similar, 10⁻⁹ meters square per second. So from the elastical restriction analysis, if you calculate the interdiffusion coefficients, they come in the order of liquid state diffusion. The solid state diffusion coefficients, there are 4 orders of magnitude smaller than that. So certainly there is a diffusion across the interface between iron and silicon, and this diffusion is much larger than it could happen between solid on one side and solid on the other side. It has certainly happened when the material was in the liquid state. It means the electronic mixing is really a consequence. Electronic mixing means the mixing introduced by the electronic energy loss, basically. This is a consequence of diffusion during the very short molten state, as predicted by the thermal spike model. So this was one of the tests of the hypothesis of the thermal spike model, which we published in 2005. What we did recently was that we did some finer corrections into the thermal spike model. We used density functional theory and experiments together to verify the thermal spike model. Consider these two equations which you have seen earlier. Usually the plots which I have shown earlier, these parameters, they are defined, they are derived from equations which come by assuming that you have metals and you have free electrons in the metal. So all these formulas which are used here in order for the computational purpose, they assume that the electrons are all free electrons. So when the electrons are free electrons, then the density of the electrons, if you see from the condensed matter point of view with respect to energy, for the free electrons, it is a parabola. But actually what happens is the density of states is not a parabola exactly. It has a lot of features in this. If it has a lot of features in this, then we cannot assume this based on the parabola, that is the free electron theory. So we have to switch over from free electron theory to exact density function theory. Now, if you have this kind of profile for the density of states, the equations for the electronic specific heat and the electron phonon interaction, they get modified. They take into consideration the whole features of all the density of states. And the electronic specific heat and the electron phonon coupling strength, now they become temperature dependent. And so this is from one of the reference where we have seen that these two components, they can change if you have different kinds of material. Now, so what we have done is we have taken a thin film composed of a combination of two things, the palladium and nickel, deposited onto a substrate which is silicon. We did irradiate these things, and we wanted to see if there is a mixing of the palladium into silicon, that is suppose the green one, the nickel into silicon, that is the red one, and the silicon into the thin film side, that is the gray one. We wanted to see. We chose this palladium nickel system because they form a perfect stress-centered cubic structure. This is called solid solution throughout the composition range. So I am not going to the details of why it has been chosen. And we did the density functional theory calculation for the density of states, G. And for different concentrations of nickel in palladium, you have a little variations in the density of states, which gives rise to various different ways in which the electron phonon coupling can change with temperature. So with respect to the composition of nickel in palladium, in one case it is like this, in one case it is like this. So there is a huge difference if you take from palladium pure to palladium nickel, and variation with temperature is also different. Similarly, you can calculate the electron phonon coupling with respect to the composition of nickel in palladium. You can calculate the electronic specific heat as a function of the composition X, and you can see that there is a non-linear variation with respect to X of these two quantities. So the specific heat and the electron phonon coupling, they vary non-linearly with X. So we expect if we have mixing between these two layers, that should also vary non-linearly. So we did XPS depth profiling after irradiation. So I am not going into the details of what these are, but ultimately the result which we get is the depth profile. When you have pure palladium deposited onto silicon, then palladium profile is like this. When you have 0.4 nickel in this, the palladium profile is this. So you have palladium profile before irradiation, after irradiation. Silicon profile before irradiation, after irradiation. So here the nickel profile also before irradiation, after irradiation, and you can see that before irradiation it is sharper and after irradiation it is more shallower. So there is a mixing in all the cases of different compositions. Thermal spike model calculations were also done, and where the calculations from the density functional theory were incorporated and the lattice temperatures were calculated. And then what was deduced experimentally was how experimentally the diffusion, the interdiffusion takes place. So there is a parameter which is the interdiffusion length square, delta square, which is in the unit of nanometer square, that can be obtained from the depth profile, which I have shown earlier. So you can see that there is a nonlinear variation, and theory also it has nonlinear variation. So theory predicts that there should be nonlinear variation in mixing, and the experiment also gives a nonlinear variation in mixing. It means if you tweak the thermal spike model fine, then you can still get the result according to the thermal spike model. So the conclusion here is that perhaps there is some mechanism. This nonlinear variation is certainly not similar to this nonlinear variation. So there is some other mechanism apart from that which cannot be foreseen, but certainly the thermal spike model is verified according to this work also, and this is a very recent format. So in the summary, I just put the same slide which is outlined. So I have discussed all these things, and then I would like to thank you.
Sanjeev, thank you for this talk. There are some two or three questions. Can you just see in the chat box and answer? And we can break for the lunch. There is one from Professor Jeroen van Koon. What is the minimum diameter obtained in ion track experiments?
What is the minimum diameter
obtained? Yeah.
Okay. This question poses
and also
some
he
more
wants
questions.
to know how does your XPSS profile compare the RBS?
Yeah. So the minimum diameter, what is the minimum diameter obtained in ion track experiments? It all depends on what is the ion energy, what is the electronic energy loss, what is the material, and then you have to maybe use the thermal spike model, find out what will be the radius of the modified material and other things. So it will all depend on the experimental parameters.
Yeah, experimental parameters.
So there could be.
Okay, the another Hemant, this one more question. He wanted to know how do get disorder fraction using RBS, and can you please more elaborate this indirect process?
So
if it is a lengthy answer, maybe tell.
So in the RBS, you have to do some specific kind of RBS, that is channeling. In the channeling, you have to have the crystalline material, and if the ion is channeled along one of the ion planes or the ion rows, then it will go undeviated. But if it is not channeled properly, if it is not in the right direction, it will be scattered more on the surface and less below. But if you have amorphous material, then for the amorphous material, whatever direction of the ion you choose, you cannot get a channel of ions, means the inter-ion space like a channel in the material. So always you get very high yield when you have amorphous material. Not only on the surface but inside also. So you have to take crystalline material, you have to see what is the RBS yield, then you have to see after irradiation if the non-surface yield is more, then it is amorphized. And from there you can find out what is the fraction.
Hello sir, I have one
more question is, can we you can ask.
Sir, can we produce oxygen vacancies or defects like that by swift heavy ion irradiation?
Yes. There are a lot of processes in the first slide I told. Lot of processes are there, and there are recoils, there are sputtering, because of the recoils there could be vacancies produced. The atoms are dislodged from their places and you have vacancies.
Oxygen vacancies can also be produced.
Oxygen is one kind of atom which can also be dislodged, right? So you can have oxygen vacancies.
Okay, thank you.
What is the minimum track that has been experimentally obtained in track under optimal conditions?
So once again, this is not a question which can be answered, because all depends on material, whether it is SE sensitive, whether it is SE insensitive, what is the value of SE, what is the ion, what is the material. So lot of things are there. So it cannot be answered in a straightforward way.
Okay, Sanjay, we are getting late, so thank you for
Okay.
coming and
Hello,
accepting
sir. I
our.
have a doubt.
Uh-huh.
So this is Neetu from NIT Jalandhar. I'm working on 120 GST material and irradiate that material on silver with the 120 MeV energy. I have a doubt
Mhm.
that you have explained the time scale of the processes for
Mhm.
Coulomb explosion model and thermal spike model. So
Mhm.
if we have a material and we irradiate with such high energy for a
Mhm.
2 minute or 4 minute time, so how can we
Mhm.
explain the defects or the if changes produced in the system based on Coulomb explosion model or thermal spike model?
Okay. So practical considerations, if you see one of the slides, if you calculate, for example, the modified material fraction, it could be amorphous after irradiation. So initially it was crystalline, became amorphous, suppose, or it was ferromagnetic, became paramagnetic. Then you can find out the fraction of the modified material. You can plot it with fluence, and then you fit it with that equation which is proposed. And from there, so these are indirect methods. So from there, you can find out what is sigma, that is the fitting parameter, which is the cross section, which is equal to pi r square. So from there, you can interpret your data.
Okay, sir.
Yeah, whoever is having questions, they can contact him via email. He has given his email address through
Yes,
chat.
yes.
So I think now, since we are getting late for the next talk, which is supposed to be at 2, so we'll close
Yes.
this session. Yeah. Thank you, Sanjay.
Sure, sure.
Yeah.
Thank
Thank
you
you.
very much.
Yeah.
Thanks.
Yeah. Bye. We'll meet
So I will
at
leave.
2.
I will leave now.
Yeah, yeah, sure, sure. Yeah.
Uh-huh.
Okay.
Oh, okay. Thank you.
Thank you.
Bye.
Bye. So we'll meet at 2. Bye.
Indra, are you there?
morning.
Good morning. Do you hear me?
Yes, very clear.
Very clear? Okay.
Yeah.
So I will try to put my screen.
Yes.
Hola. I have something. I am from Latin.
Ambuj?
I have some Larsen in
Yeah.
my phone.
No, Ambuj. Okay, now it's fine.
Ah, okay. Thank you.
Am I audible?
There's a
Sorry.
lot of echo
Hello,
and
Ambuj.
sound is there, Ambuj.
So, hello. But sorry, I have some Larsen on your in my phone.
Yeah, your phone is okay. Ambuj.
No, because Ambuj was trying to contact me
Yes.
and to say hello to him, but when
Yes,
he
yes. It's
put his
vibrating.
micro,
Yes, yes.
yes. So I'm trying just to
Present
put
your slide.
slide,
Yes.
partager,
Yes.
partager.
करके आ गया हाँ
Is it okay? Hello.
it's okay. Yeah, it's fine.
It's fine.
Yeah, looking nice.
Yes, yes.
Okay. So I'm just trying to see. Okay. If I don't put full screen, yeah, I may. If I should put the full screen. Yes. Okay. This is the best. So I'm just waiting your
Introduction.
yes.
Then we'll start.
Yes. That's okay. But
Okay, we still have 6 minutes, but Ashokan, my voice is coming clear because I thought there was some echo earlier.
Now it is better. Now it is better.
now
Before
it's
it was
okay.
echoing.
Hello, Amboj. How are you?
Wow, fine. You're looking good.
I will try too. It's begin to be the age is begin to be on my shoulder.
And you have got a
That's
nice
it.
photograph also in that talk.
But this is Brittany. When I go just during summer, and we get this. This is wonderful. I like a lot Brittany because this is not too hot. There is not a lot of people on the beach. It can be. We can sometimes we can be on a very large beach, only 100, and we have more than 20 meter each side without any problem. So this is good. I like that. And this is Brittany, which is wonderful country.
Yeah, okay, looks nice.
Just to send to you some wonderful part of France. But I do regret not to be in your Inter-University Accelerator Center, but this is a situation that does not allow us to meet together. That's a pity.
Good afternoon, Marshall sir. I am Indra here.
Yes.
Sir, in your presentation at the bottom side, you can see that you can hide that bar so that it will not come in any information you would like to share in the slide.
Masqué. This is
This
what I should
message
do.
you can hide.
Okay, is it hidden?
Now, yeah, it is not visible now. So this is better. So now it's your full screen is properly visible.
Okay. Thank you very
sir.
much.
Yeah.
No. You should drive me. Because this is the first time that I do something like this. So that's it.
Yeah, at one time we had thought, I was telling in the morning, at one time we thought we will cancel it and not do it, but then we thought everybody is getting used to, so we also should try to do it online. So finally we decided to go online, so both the school and the conference. So now we have doing both online.
This is a good idea. This is a good idea. I know that my son, which is at the Bordeaux University, is making a lot of teaching lectures using video. But as I am not a teacher, I don't make any video.
Yeah, we also, I recently made a couple of lectures for this type program just to see, get used to it in case this goes on for longer. So
No, I
getting
don't.
used to-
I don't. I don't think so. It could be 1 year, but not more. I think so. I think that they will found the counterpart of the coronavirus. I think so.
Yeah, maybe 1 year, that's all.
Yes. Hmm. Azokan?
Ashokan?
So I should escape. Should I escape? Perhaps to see if he's here. Ah. Hello.
Yes.
Azokan, did you?
Yes. Yeah, I'm getting your voice. Yes.
Did you contact Samit Mukherjee?
Yes, I have sent a message. Morning,
Okay.
I sent a message. Yeah.
But I will try to Skype with him, whatever it is.
Okay.
Don't worry about that. So Furhan, I see you. Hello.
Foreign?
Yeah, good morning, sir.
Good morning. How are you?
Yeah, I'm good. What about you?
Oh, wonderful, whatever it is. All my family is okay, so this is a good thing.
Oh,
This
that's
is the
great.
best. No problem in my family.
Great.
Yes. So I go back to the presentation because now it's time.
Yeah, it's becoming 2 o'clock. Indra, I think some people have not logged in again, so but maybe we can.
Sir, you proceed with the proceedings because he has to start at 2. So kindly introduce him. I will follow.
Okay. So Ashokan, shall we start?
Ambrose, will you be the chairman?
Yeah, I will just get it started. Yeah.
Okay.
So I will just introduce you and a couple of minutes, and then you can start. So.
Okay. I just wait.
Okay, Ashokan.
I think maybe another. Yeah, you can 2-3 minutes. You can.
Maybe just 2-3 minutes because I think some people are still logging in.
Yeah. Yes. You can wait. I think.
Just
When the number crosses 17.
Yeah. So.
Maybe you can introduce him. Then another 2-3 minutes will be there. Ambush.
Yeah. Okay. So, yeah, my voice is clear now. No? So, okay. So, good morning, everyone. Good afternoon. So now we are in that post lunch session, and I hope you people have the quick lunch because last session was a bit late, but we don't want to delay this one, so we will get it started anyway. And we are lucky to have a very distinguished speaker in this talk, Professor Marcel Toulemon. He is the first thing I would like to tell about him is that he is the fittest young person at 77 that I know, and he has been
Go ahead.
more and he is active in research for more than what most of the audience I think median age will be. So you are all lucky to have get this lecture from one of this experts in this field. And many a time you will see in our papers thermal spike model we uh, use. So that is his first introduction. We have been he has worked on that, and we many of us have been using it. You will see in our publications that. So that is the second part. But just to start for the beginning, he has been from the University of um, he started his career in Nancy University and Strasbourg, and then he did his PhD in I think after 6 initially he was in nuclear physics, then he shifted to material science. Around 1974 he did his PhD thesis and his doctorate in science, and then most of the time afterwards he has been at CNRS. As you know, he has been visiting scientists in many places, but he has mostly been at CNRS as is one of the you will be knowing is a major research facility. So is it what we refer to here is as you can say equivalent of emeritus scientist or director of research emeritus as CNRS, and this is a permanent member of CMAP. So which is then again this this major laboratory at CAN. So I think he has been there in this position twice as the director of research emeritus for 2 successive terms, and he has still been very active. And as I mentioned in the morning session, he is one of the people who have been associated with us for a long time, and he has been visiting also IUAC many times. And we also had one of our colleagues had managed to involve him in a road accident also, so he has been so frequent visitor to IUAC. So we are very happy to have him here, and let's listen to from the expert. He will be talking about this damage induced by electronic excitation with swift heavy ions. So in the first part, he will mostly be talking about this damage, and the second part, he will be talking about the models for the description of track formation. So Professor Dr. Toulemon.
Thank you very much, Amboj. And it is a pleasure to participate to such kind of school, not summer, yes. I'm disappointed not to be in New Delhi, but the circumstance is out of sense for a moment. And we shall try to communicate, to exchange our knowledge in order that each people will be happy to know several other things. The first picture that you see, this is a part of Brittany, west part of France, when it is a very quiet time and a wonderful country when we can have our summer time. So I will divide my presentation into talk, experimental determination of a damage or material modification, and the second part, which is mainly on transient thermal process. I don't know how we can interact with such kind of things. We will see, but I will, in the first time, to try to talk about 40 minutes, 2 times 40 minutes, and stop in order to have some question if you want to have it, if you need to have some more explanations. I begin by the experimental determinations because I am a physicist and an experimentalist physicist. And from my point of view, experimental part of physics is one of the most important things. I like to say that if you do a very good experiment, well done, well prepared, with a quiet answer, yes or no, from the point of view of experimental, this will be something which is stable and will stay all the time. Now, if I go to the second part, this is a transient thermal process. This is model, and model is evolving with the time, always. So as an experimentalist, it is very important, as I say that to any of you, experiment should be very powerful with a clear answer, yes or no, about what you do want. And in material science under irradiations, 50% of the work is done before the irradiation. So now if we go to the ions, to ions, whatever it is, we have three kind of damage. This is the nuclear damage here. This is very surfaces. You have high charge ions, which are very low velocity, which deposit a very high charge on near the surface. You have swift heavy ions, which go very, very long. And you have femtosecond laser experiment when you do excite electrons. I do learn a lot from femtosecond laser experiment in order to understand the damage in materials due to swift heavy ions. I encourage you also to look what is going on femtosecond laser and material transformation in order to understand how thing is going on. We get the biggest advantage as compared to femtosecond laser. We know what is the energy which is deposited in the materials. We don't know exactly what is the volume in which it is deposited, but we know exactly in the energy which is deposited. So, and this very difference, this is a cooling rate. This is very short in this regime. It's 1 order of magnitude longer for cylindrical, and femtosecond laser is a planar deposition, so this is this. So you can quench some phenomena in with swift heavy ion that you cannot see with femtosecond laser experiment. When we are dealing with energy depositions, I come back now to the energy and the specific, just to give you some feeling. Energy loss is given by Ziegler and Grande and Chivist, and you have also the nuclear energy loss by Ziegler. And the nuclear is at low energy, as I say, around 10 to minus 4 MeV per U. The swift heavy ions are on 1 MeV per U, and here this is 10 to minus 3 MeV per U. Okay, so this is to say that we have in 2 different kind of regime, and when we are at very high energy, we can not forget about nuclear collisions, but this is negligible. Now I'm going to work on that, the swift heavy ions. And just to say to you, I am in Caen, in the CMAP, and the CMAP is on the Ganil accelerator. The CMAP is doing photonics and ion matter interactions, is in Ganil accelerators, and if you wish to be welcome, the welcome of the Ganil is done by this guy, Jimmy Rangama at ganil.fr. So I think that you have received my lectures. Some slide will change a bit, but you get everything in your slide. The director is not now, we just changed the director. The director is Isabelle Monet and not Amin Kassimi. This is the Ganil accelerator, which is here. This is a CMAP, which is in 3 different parts of a campus university. This is an engineer school here. And you have an irradiation with high charge ions at low velocity here. You have one MeV per U here, and you can have here either 10 MeV or 100 MeV per U. So we can cover all the range of energy of ions in Ganil camp. This is the accelerator that you have here. This is an injector, and you can extract the beam in this direction and you get 1 MeV per U. And this is when this one is working for the high energy, the other one is working for the other IRSUD. Then you go to a first accelerators, you get a stripping, and you can extract beam to go here, which is a medium energy line, which is around 10 MeV per U. And the other part is accelerating in the other. You get an alpha spectrometers, and you go here back. This is for radioactive species. So when we are dealing, with energy depositions, we deposit the energy on the electrons. The electrons are ejected. Then you have a cascade of electrons. And all this is done in 10 to minus 14 seconds. And the energy is shared on the electron in a certain volume that we have to determine. And then this energy is shared to electrons, transferred to lattice. And this is a big question mark that I want to answer. So this is, you have in situ experiment with a corresponding time. In this regime, Auger spectrometry allows us to probe the temperature, the electronic temperature in this time. Then in this time, here, you have a sputtering of atom. This is to say that you have atom which is ejected from the surface of the materials. In this time, you get the later track formation, and then at a longer time, you can have some chemistry. And more of the time, you are looking at a very long time. This is to say, you don't know exactly how the quenching was done. So, I want to show different parts. The first part is a direct determination of track radius by transmission electron microscopy and track morphology. I think that you get several parts of this, several explanation of this talk by Dr. Srivastava just before me. Then you have scanning force microscopy, who measure the radius of a track at the surface. You could have also small angular scattering as an example, which allow to measure the bulk radius either in a 10 micrometer or 1 micrometer, depending if you are in grazing or perpendicular incidence. So this is a direct determination here. Small angular scattering, sorry, this is not true. Small angular scattering should be here. I make an error here, sorry. So small angular scattering is an indirect determination of the track radius. And you measure the material transformations as a function of affluence, and then you will see later on that we can extract a cross sections. And the problem is to see, does the cross sections correspond to a radius of a track? We have a lot of several physical characterizations. I will talk about sputtering, and I will show you 1 or 2 examples when electronic and nuclear can be combined in defect creation. This is the electronic energy loss now with ions. And you have the keV per nanometer, the beam energy. And if we are using 1 to 10 MeV, we can reach the maximum of the electronic stopping power, but at high energy. And another time, I repeat all the reference here. All the reference is quoted for each slide as much as possible. Now, I go to carbon cluster. And carbon cluster can be delivered for ions, but allow us to have even larger electronic stopping power than the maximum that we can get with heavy ions, but at low velocity only at low velocity. And you will see what is the interest of a low velocity as compared to the high velocity. And this allows us to see some other phenomena that we cannot explain cannot explain from other determination. So, transmission electron microscopy, mainly presented by Srivastava. I just want to come back to just whatever it is, a material, insulator, a semiconductor, metallic system, we have track. So if we have to understand why and the reasons of the track formation in all this kind of material. I want to point out this phenomena, which is the velocity effect. If we look track with an irradiation at 7 MeV per year, you get all the things here, which has been presented in this paper, nuclear instrument method, and you get a track size which is of this order of magnitude around 5 for 40 kV per nanometer. You get the same track size at low energy, but for a lower electronic stopping power. This is to say, going to low velocity, you get larger track. But the problem, at low velocity, you cannot reach this 40 kV per nanometer. That's why you can go for 50. That's why you can go to larger track as compared to this. But the efficiency of track formation using ions is better at low velocity. You get the same thing in calcium fluoride also. 0.1 MeV, which is Janssen, and 9 MeV, which is calcium. So this is a very specific phenomena. Velocity effect does exist, but we have to understand later on how this can interact with track formation. Now, scanning tunneling or force microscopy. You have a mica, which is force microscopy, ENP, which is force microscopy. Here, this is tunneling microscopy. We measure the electricity. Carbon graphite, this is also tunneling microscopy. Yttrium iron granate, which is force microscopy, because it is difficult to measure a current on between tip and materials. I'm going to go a bit deeper on such kind of technique. So I think that you know that, but at least this is a tip which is going on the surface. Then you have a laser and you reflect the light which is on the tip on a photodiode, and then you have a detector and feedback electronic in order to map the surface. And by moving that, you move the light reflectivity and you can map the surface. This is what it is done with mica by these two researchers. I go to the mica just to show what are the measurements that we can have as compared to some TEM. Mica, this is a lamellar materials, and there is nearly no swelling, because there is so much difference between two layers that the mica can expand if it is in disorder. And you get such kind of picture. If you go to TEM, that you have here by Vetter, you can see track, which is wonderfully observed as compared to force microscopy. But you'll get something a bit smaller, but within the experimental error, we can say you get a good evolution of the track size in mica at high energy. And the other was done by Buffard, and we get something like this. So there was some differences between the two measurements. Just to show, this was the oldest experiment on track formations, and this shows you how difficult it is to be sure that we get a good value of a track size at the surface of the mica. I am going a bit further on another materials, which will be the calcium fluoride. And the first thing that we have done is just to measure the number of phyloc created as a function of the electronic stopping power. And with ELOC efficiency, this is the number of phyloc divided by the number of ions. And we arrive to an efficiency of 100% only above 17 kV per nanometer. This is to say, this regime, we don't have all ELOCs, all track does not create an ELOCs. This is perhaps linked to what Dr. Srivastava showed you that the discontinuity of a track can decrease the number of ELOC that we can have at the surface. If we have no track, if we have a discontinuity, there is no track at the surface. But at least we see that, which is wonderful, which is very clear. And we can, this is very easy to do that. We just have to count. Now we have the same thing at low velocity, which has been done by Wang in 2014. You can see it's not too old experiment. And another time we can see that in the efficiency, we get another time the evolutions of a velocity effect, going from high energy to low energy, we get a better efficiency of track formation. Now, if I want to measure the radius of this is something which is difficult because you have a tip, which is a certain size, you have a ELOC, and if the tip is going like this, you measure that. Something which is larger than the object. This makes difficulty to measure the track size on the surface by scanning force microscopy. So what we have done with Kalfawi, this is the following. We plot the height of each ELOC as a function of the measured diameter, artifact diameter, and then we can see that we have a kind of correlation which allows us to extrapolate to height equals 0, which gives us the tip diameter. So we can deconvolute the size of the track here by the tip, that the radius of the tip, and extract a complete radius, exact radius, taking into account the difference in size. And that's what we get. This is Kalfawi in tapping mode. This is in contact mode Muller, a bit larger. We don't know why there is some difference. And TEM, which is smaller, clearly smaller. So this is the question, why there is such kind of difference between TEM, tapping mode, contact mode, and transmission electron microscopy, radius as a function of electronic stopping power. Remember, in mica, nearly TEM and contact mode give the same radius. So there was a recent experiment which has been done by Ishikawa, who tried to see the evolution of the ELOC appearing at the surface of a calcium fluoride. Here, you can see wonderful picture. You can see the high resolutions. And if we compare this, you get a radius of 12 nanometers. And if we compare the two tapping mode, we get something which is equivalent to what we have observed. But now the questions that we have, why it is constant, we don't know. And this is open questions. But at least we get something in tapping mode if we take into account the size of the tip and we take that out of the, we deconvolute from the ELOC size, we arrive to a good value. Just to show you, this experiment was also done in CO2, and we can see ELOC at the surface, this was a thin film, and the track inside. Another time, we see that the track inside from electron microscopy seems to be smaller than the ELOC. So we see that we can have some difference between bulk observations and surface observation. Does this correspond exactly to what we can expect? This is the question. And we see also the same thing in this paper. So this was ionic crystal, non-amorphizable. This was also a non-amorphizable material, calcium fluoride is non-amorphizable. So the difference between amorphizable, like mica, and non-amorphizable material is the following. The surface, the track at the surface seems to be larger than the track in the bulk. we have to solve this question. Just small angle X-ray scattering, which allow to see what is the difference in electron density along the track, and this was used to by Kloot and by was previously used by Albrecht and Kloot and applied to amorphous ion boron by Rodriguez, and this is the oscillation that we can see. Larger are these oscillations, smaller are the oscillation, larger are the tracks. And we can see something which is like this. This is a direct observation. This is not a direct observation, but this is a direct determination of a track size, because we don't take into account the fluence, and that we need just to have a low fluence just to be sure that there is no overlap. And scanning force microscopy was done by Audouard, and within the experimental error, we get something which is equivalent to surface.
Your mobile, your speaker is muted.
Professor Suleiman, you are muted. This might be on the screen. The symbol might be there. This microphone is symbol. So you have to click on that. Maybe it is.
Amboj, this is Tapo. I mean, I saw that on the screen. Rahul had muted Marcel, and Rahul had left the meeting. I don't know who is this Rahul. Please take care. It's something beyond Marcel's control, probably.
Okay, Ugra Mohan, you can just unmute him.
Hello, Ugra Mohan, are you there?
Yes, ma'am. I am
Please
trying.
unmute. Okay, thank you.
You just try to unmute him. Marcel, you just wait. We are trying to look into it, how it has happened, if it has happened on somewhere from this side. Or if you can, I think you should still be able to do it from your screen. There will be.
Yes, Marcel sir, you have to be first stop presentation, and then you can find the options at below. Yes, sir.
Okay.
Yes,
You hear
sir.
me now?
Yes, sir.
Yes?
Yes, sir.
Yeah,
Fine, sir.
okay.
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 I don't know what. Oh, yes, I understand. So, présenter? No. No.
Hi, Marcel. This is Tapo. Everything is fine, Marcel.
Yeah. But I'm trying to go back.
Yes, sir.
Do
This
you
one.
see something?
Yeah, you are back
Yes,
now.
sir.
Yeah. Just please make it
Okay.
full screen. Yeah.
Okay. So if I just say to you here, small angle X-ray scattering, we measure the difference in density along the track, and scanning for microscopy at the surface, bulk and surface, and we get the same track radius. Now in amorphous SiO2, this is a bit more complicated. It was not possible to fit that with only one track size by small angle X-ray scattering, and this is a Sachs radius as a function of energy loss, and we can extract two track radius, one which is a shell, one which is a core, and we have to understand that. And this was confirmed by transmission electron microscopy by Nakajima, who do irradiate thin film of SiO2, amorphous SiO2, and when he's looking by TEM, he sees something like this, and by HADDF TEM, you see something like this, showing that there is in the center a hole and kind of overdense material, and then a shell and a core. And this was confirmed by them, by TEM here, though. So two tracks, radial morphology appear in such kind of track. So what I can say is track size TEM and SAX seems to be okay. TEM and SEM not for CFD, but yes for Mica. So depending if you are amorphizable or not amorphizable. But the problem is, can we get a track threshold by TEM and SAC? This is the questions. Until now, we get always some difficulty in order to see a threshold of track formation. As an example, if we here we were not able to measure any observations in source here. This is not normal. If we extrapolate like track radius, it's something like this. We don't have something which is just a line to guide our eyes. Now, indirect observations. This allows us to use a lot of different techniques to measure the track size. Either Rutherford backscattering, like here, when you have a damage near the surface as a function of effluence for lead irradiating yttrium iron garnet, and you can see an evolution, and you reach a complete amorphization after effluence of 1.5 10 to 12. You can have a wide angle scattering in bulk, which has been done here by Grigiel on strontium titanate, and you get something which is like this. This was a very precise experiment. This is just some point which has been taken just to be sure that this is okay. You can have Mossbauer experiment. I'm going to go further. I think that Dr. Srivastava showed you how to extract. Swelling measurement. This is very interesting because you just see the swelling of the materials. If you introduce defect inside the material swell. And you can see directly that at the surface of the material, you measure a step when a part of the material is irradiated and another part not irradiated. And this is the paper of Trotman here. Electrical conductivity, you have Dufour, which is very interesting for metallic system because you are obliged to do that because you have to make the experiment in situ at low temperature for metallic system. So we use all these different techniques in order to follow the evolution of a damage as a function of effluence. And using a statistical law, which is this one, Y is equal to Y max, or 1, depending on things, multiplied by 1 minus sigma phi. Sigma, this is a cross-section of a damage creation in the material transformations. And you can extract that for using all these different techniques without any difficulty. But this is a cross-section which is devoted to RBS, which is devoted to X-ray diffractions. And you should be sure that this is not a clear determination of a track. And I show you that microscopy was shown by Srivastava, and this is the RBS. This is the paramagnetic phase, and we can see that within the experimental error, all these techniques give the same things, and we can say that yes, the radius is the square is following the square root of the electronic stopping power, and this is a clearly low. This is a law that we should have in mind for track formation inside materials. If I go to track in amorphizable material now, we can see you have SiO2 quartz, mica, yttrium manganate, gadolinium titanate, and we see an evolution of the track diameter. And this is the questions that we should understand. You have all the reference here. Yttrium iron garnet, virgin, and it is a non-amorphizable material, and you see a new phase which appear here. This was done by this. Get the same thing for zirconium oxide, hafnium oxide, when we get the fractions of a tetragonal phase which appear in this material, which is not inside. The questions which is open is it nanograin formation, which is not non-stable in the initial phase due to the competitions between surface energy and bulk energy. When you have very small grain, the energy of the surface of the grain is in competition with the bulk energy, and to stabilize the grain, it is obliged to change the structure of the material. Comparison amorphous versus crystalline. It seems that here we get the same, here we get smaller. From amorphous to non-amorphous materials, you would get an increase. It seems, it's just not a very clear idea that non-amorphizable material is more difficult to create track inside. It seems, I underline that. Energy depositions. This is important, velocity effect, because here we have a clear expressions of what is the velocity effect. So at very low energy, this is the track size as a function of electronic stopping power, radius as a function of electronic stopping power by Jensen. When I go to 1 MeV per U, no difference. And I say to you that there is a velocity effect. I go to 15 MeV per U, we get a difference. And this is the questions that we have to solve later on when we develop a model. We see the same velocity effect in amorphous SiO2. Track radius as a function of electronic stopping power, 5 MeV, 0.2 MeV. This exists in a lot of different material, as you have here going to this. Radial morphology by X-ray diffractions. Calcium fluoride have shown to you that surface track is larger than bulk track. If we measure by XRD the evolutions of the damage inside the X-ray, which correspond to 1 micrometer, we see two phenomena that appears. The line of a peak is increasing with the electronic stopping reverse fluence, and we can extract cross sections of increasing the width. And also the area of the peak is decreasing when you increase the fluence for an electronic energy just larger to that. And then we get two track inside. This is a change in a nanograin here. This is bulk change in crystalline phase. And if we compare to RBS, which has been measured for calcium fluoride, you can see that the disorder observed by RBS is the same than the increase of the width by XRD. This is go to this reference. You have a lot of detailed information regarding these evolutions. This allow you to understand how we have been able to understand this. And now if we go to high resolution electron microscopy, what you have seen, this is bulk, this is surface. And so we are in surface. And this is to say that TEM in bulk is not able to see the track inside the calcium fluoride, but only at the surface. So this shows you how TEM is also sometimes very difficult to use in order to understand the track formations, but very powerful. Material sensitivity. So you can see how thing is evolving, track radius as a function, this is different. And insulator, nearly all insulators are sensitive to the track formations. If I go to metals, this is amorphous materials. And the surprising thing was to see by Klamunzer that we have this is the initial part. This part is not irradiated. This one is irradiated. And you can see an anisotropic growth, which corresponds to an increase of the resistivity of the material, which is like this. Now, if you change the angle, you arrive at a situation that you get a saturation of the resistivity due to the fact that you decrease, you change the form factor to determine the resistivity. And we can extract the track radius from that. We have chemical exchange in amorphous iron boron, which has been shown by Trotman. Surprisingly, this was also a phenomena which were not observed before this year, and atomic force microscopy, as I shown to you previously. And this is here a track radius extracted from electron resistivity measurements. You measure the evolution of resistivity as a function of fluence, and you can then extract a track radius. SAX is okay within the experimental error. So SAX, which is a decrease of density inside in the track, agree with the size of the track in which we have a resistivity. The resistivity says that you increase the number of vacancy along the ion track. Chemical etching is efficient above this value, and you have seen that in talk of Srivastava. This is efficient and this is not efficient. Difficult to make a chemical etching. So we need to have large track in order to make a track etching. Now, crystalline material, there is a lot of work which has been done in the beginning of the works. Nickel by Ivazé, when there is defect annealing, defect creation in iron by Dunlop, amorphization of this material by Audouard et al., track in nickel zirconium by Barbu et al., damage in bismuth, and was a very good test for the transient thermal process that I shall explain later on. You get a fast change in latent track going to alpha titanium with C60 beam. When you go to very high electronic stopping power, it seems that the recrystallization does not appear as it was previously. You get sputtering in metals, and I will show you later on. And a lot of publication of ITC superconducting materials, which has metallic materials. So now these three materials, titanium, bismuth, irons. This is a bit surprising to see how we evolving the radius. Titanium has very low electronic stopping power, but not a large track. Bismuth has a larger threshold, but going to very large track, and iron is smaller track and smaller threshold. So we need to understand how this which parameter can explain that later on. And amorphous iron boron is more sensitive than crystalline iron, and this is a systematic phenomena. Amorphous materials is more sensitive than a crystalline wine, despite the fact that in an amorphous material it's more difficult to observe a track because we don't have a contrast of amorphous phase inside the crystalline phase. But small angle rescattering or resistivity measurement was a very good tool to observe this track size in an amorphous materials. ITC superconducting materials is in between the two, not too large track, but a smaller threshold than bismuth. And if I look to that, when we have nearly the same electronic stopping power for the uranium beam energy varying from 4 to 12 MeV, we see a decrease of the track radius as a function of the beam energy. Another time, we get also velocity effect inside irons. And in bismuth, this was one of the most powerful experiments to show that temperature of a target can change the track size. We were around here and here, and this is a track size which is increasing if you increase the temperature of the target, and vary from nearly 1 order of magnitude for this point. So we have a temperature effect in track formations, and I think that you have seen such small effect of a temperature effect in yttrium iron garnet in the talk of Dr. Srivastava. Metals, and important, copper, silver, platinum, nickel, niobium, non-sensitive. These ones are sensitive. Amorphous materials, whatever it is, are sensitive. And this is track values as a function of energy loss, crystalline amorphous, ITC bismuth antidote. And I try to correlate this color with the references. Semiconductor. How much time it's yes. I'm going to stop here 5 minutes if you wish to ask me some questions. Then I will go to the second part of semiconductor and the combination of nuclear and electronics doubling power. So if you have some questions, you can ask me. Hello? 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 No question? I should continue?
Yeah.
Right. I get some. Okay. Good.
Yeah, it's fine now.
Yes.
So, Dr. Marcel, can I make a little comment?
Okay, go ahead.
Regarding this cross section, I think we need to make a comment that whatever the assumption, that is for the single ion impact only.
When we have with TEM,
yeah,
scanning force microscopy, this is always single impact. Okay, and the cross sections is mainly single impact. Sometimes you have a two impact parameter. As an example, if I go back to I should
So this PPT is minimized, so you click on that minimized. जो नीचे minimize किया है PPT, just click on that PPT.
PPP, I don't know where is it.
This presentation file.
Arrêtez la présentation, okay.
Present.
Okay, so but I want to go back to the presentation to show something.
So on your computer, this presentation is already open, so you click on that from the down ribbons.
Okay.
But now you have stopped presented, I guess.
Now, is it okay?
You have to present again. Yes, it is coming.
I have to present again.
It's coming. It's coming. Yes.
No, it's coming. It's coming. Do you see it?
Yes.
Yes.
Yes, I can see.
So I come back on one slide. This one, which is in the paper of Peña-Gub and Physical Review.
Yeah.
This is you. If you are so, let us see. If you have a direct impact, you get something which is like this, which is a proper evolution of a damage. Now, you can have something which is changing at the beginning. As you can see here, which is not something which is like this. This is something which is going like this.
Right.
And this is a two impact phenomena. This can be expressed as a two impact phenomena. The question is the following. What is the transformation of the matter due to the first impact? Till now, nobody has explained that clearly. Do you have two phenomena that appear at the same time? I don't know. Because this is to say that you transform the material here in order to increase after the transformation.
Right.
So this is not, the initial phase is not something which is clear. Okay?
Right.
Thank
you.
Other question?
This morning there was one question. What is the minimum diameter that can be obtained in ion track experiments?
In transmission electron microscopy, I think this is 1.5 radius. And this is a sphere. This is the work of Chantal Huppert, which has been shown by Dr. Srivastava. With TEM, you cannot see something which is smaller. And I think this is due to the fact that the energy deposition is a statistical law, and sometimes you don't have enough energy in order to create a track. Now, if you use an indirect method, you can measure a cross-section and you extract an effective cross-section which can be smaller than 1.5. And this is what we have in this here, which is very low in radius, because you are able to measure a cross-section, which is very small, but this is only a cross-section. So directly, minimum value is 1.5 radius. Indirectly, you can go to lower value of cross-sections. You have an effective track radius, if we transform that in track radius, but at least you can extract a threshold. If you plot that square of a radius, you have something which is a cross-sections, and you have a threshold, and the threshold will be here. So the indirect method allows us to have a determination of a threshold of track formation inside a material. Okay?
Yeah, it's okay. You can continue.
I can continue.
So
Okay.
there are few more questions which are written in the chat box.
Oh,
So would you like to take? I am just reading it for you.
yes, please. Yes, go ahead. Yes.
As you mentioned, the direct methods to measure the track radius directly using HRTEM and SAX.
Yes.
In your opinion, which one is more accurate technique?
The two are very accurate, whatever it is. If you do high resolution microscopy, you can have atomic resolution. And small angular scattering, this is a statistical method which smear out the difference in the track size, and you can have a very good value also. The two are very, very efficient, but the difference is due to the fact that SAX is measuring only the electronic density change. TEM observe all the atoms displacement.
Okay. So next one is in high resolution TEM images, we get not only track diameter but also the structural information.
We can have that also. Yes.
So I think that is the advantage over SAX, STM.
No, SAX, small angular scattering, you can also see, because if I go back to amorphous SiO2, I'm going to try to go quickly there. Better to go like this. This is here. You have a two track size at the same time.
Yes. So how these two track sizes are we are getting?
It's coming
one
from
is the core and one is the halo.
Exactly. One is the core, one is the halo.
Okay.
And we see that by infrared measurement that the halo correspond to the transformation of amorphous SiO2. And the core, we cannot see that by infrared, because when there is no matter, there is no infrared absorption.
Okay, another question by Taranga Dehuri. He wants to know whether the diamagnetic thin films can show the ferromagnetism after swift heavy ion irradiation.
Sorry, could you repeat?
Yeah, can diamagnetic thin films show ferromagnetism after swift heavy ion irradiation?
But this is there is an example from Studer and Hall on I don't remember which is spinel. When we go from a dynamic to magnetization, and this is due to the fact that we create a nanograin, and this nanograin is not stable in the initial phase and transform an exchange in the different species in order to create a magnetic phase. This is mainly due to the fact that you have a from my point of view in this case, nanophase materials. This guy should perhaps send me a mail in order that I send him the information. Okay.
So, Mr. Tharanga, you can, if you have heard him, please send a detailed email to him so that he can understand the problem and will respond to you through that. So, any others to?
Okay, thank you.
Yes. No, I go now. I should continue now. So we go to semiconductor. Semiconductor is for me still a problem. You will see. You get wonderful image by Vetter and tool on this semiconductor, germanium sulfide, and this is elongate track. There is a controversy on these images. Some people have done some other measurement, but that did not publish it. This is a bit surprising, but don't see these elongations. But at least you get a wonderful image because you can see, if you can see the high resolutions, you can see the amorphase. This is very wonderful definition of the track size, and the radius as a function of electronic stopping power is following that. This is germanium. Then you get another semiconductor, indium phosphide. The damage have been measured by RBS, by Kamaru, by Welsh here, and you get something which is like this. And we have to understand why indium phosphide is less sensitive than germanium sulfide. Now this was done with ions. Now if we go to cluster, and we use this cluster to irradiate indium phosphide in order to see track. And this experiment was done by Damadohan. And you can see track size here, wonderful track. You see this paper. And you get this track radius, which is quite larger than the expected indium phosphide. Another time, we see that velocity effect can play a significant role in the track formation. If we continue with cluster irradiations, because germanium, silicon, gallium nitride was not nearly not sensitive to heavy ions. Germanium, no. Silicon, we don't see anything. Gallium nitride, I have to look back, but at least these two, germanium and silicium, no track by swift heavy ion, even at the largest electronic stopping power. So cluster was a very powerful tool in order to see this track. And then I plot here the different track radius, indium phosphide, germanium, gallium arsenide, silicon, gallium nitride, aluminum nitride, and all the references are here. And you can see that we see a very big differences in the track size, from 2 to 10, factor of 5. And this is what we have to understand. Apart indium phosphide says no track for ions with a mass less than lead and only with C60. So semiconductor like this was sensitive only to very high electronic stopping power, and mainly low velocity. This is a question that we will see later on that we cannot understand. But in semiconductor, we can see that for ions, silicon carbide, silicium, germanium, gallium arsenide, aluminum nitride, not sensitive. This one is sensitive. I don't know why. Because this is silicium and germanium not, but this one is sensitive. Germanium sulfide, indium phosphide, gallium nitride are sensitive. Amorphous materials, sensitive whatever it is, and always with clustering. So this is surprising that semiconductors are less sensitive than metallic system mainly, and quite less sensitive than insulator. This is a question that we should solve, and I think I will not have any answer, but you could think about that later on. So just trying to remember at which time I have to stop. Okay. It's okay. 10h55. Okay. So conclusion of material sensitivity, metal, semiconductor, insulators, mainly seems something like this. Mainly, but competition between semiconductor and metal, which is the most sensitive, we don't know. Sputtering, the interesting of sputtering is independent of when you make a track, you move atoms and then atoms reacts. And sometimes the relaxing of this atom can perhaps completely recrystallize. But if we make sputtering, recrystallization does not have any effect because the atoms are expanded out of the materials. And we should be able to measure something which is perhaps different. This is a bit complicated for semiconductor because mainly you have an oxide surface which seems to increase the sputtering rate. But at least this could be an idea. But here I see an experiment when we have a catcher, we do irradiate, the atoms are emitted, there is a catcher, and then we make the analysis of the catcher. This is and we measure here for sputtering for crystalline SiO2, amorphous SiO2. Another time, we see that amorphous material is more sensitive than crystalline because the sputtering rate is larger than SiO2, than the crystalline one. In titanium, this is a bit more complicated because we need to have this is titanium. You need to have an ultra high vacuum system, and you need to measure in situ the appearance of an oxygen layer. And this was done in a 10 to minus 10 bar or 10 to minus 6 Pascal. And you can measure at the same time the ERDA, which show you if there is an oxygen at the surface, and if there is no oxygen, you measure the sputtering rate. And this is done by Miskes. I don't know where is it. I forget the references here. Miskes, and you have two references regarding the sputtering rate and resume. So if I show you a comparison with track size, here this is the track size of amorphous SiO2 and the sputtering rate of amorphous SiO2 in blue, and in red crystalline SiO2 and sputtering rate of crystalline SiO2. So another time we see that crystalline is less sensitive than amorphous. This is the same sputtering rate also, but the threshold here it's around 1, here is around 6. So the threshold of sputtering rate is larger than the threshold of track formation. This is a bit surprising as compared to nuclear collision. The energy to sputter an atom by nuclear collision is around 5 eV. To create a defect inside the material is around 25 eV. So this is 5 times larger. So this is in contradictions with nuclear stopping power, and this show you that we have a very specific phenomena that appear in the track formations by electronic excitation. So you have some calcium fluoride, you have the calcium and the fluoride that you can measure independently very properly, and you have here the titanium, and you have here a lot of different material, and the surprise, and you can see zirconium, titanium, gold, uranium, silicon from a crystalline SiO2, silicon from amorphous SiO2, calcium fluoride, lithium fluoride. So you can see that you have nearly 4 orders of magnitude change in the sputtering rate. This experiment was done by Kahn in Munich, and this was very powerful to use the carbon-13 in order to be sure that contaminations by carbon-12 at the surface does not affect the sputtering rate. So you can see you have a very big difference between all these, and we have to understand this later on. So material sensitivity, you have a longitudinal track for morphology, spherical, elongated, and continuous track, increasing the electronic stopping power. You have a radial track morphology, so you can have a core shell track. You have an ion velocity effect. This is a low velocity is more efficient than high velocity. Temperature effect, increasing the temperature, you increase the track size, and the sputtering is less efficient than the track formations in point of view of energy density. So this is what we have to understand later on when we go through the models. So this was, I think that you have this slide, but this was all the collaborators with whom I have worked in order to get all this information, and some PhD students all along my life. Now I want to say two words about material sensitivity, material multi-layers. Tungsten is no, I make an error here. This is carbon. Sorry, this is carbon. Crystallizations of this multi-layer tungsten carbon used for reflection of X-ray in synchrotron light. So this, you see a recrystallization and a mixing of these two. Nickel titanium is mixed, okay. Nickel is not sensitive, titanium is sensitive. Fer terbium, this is the same. Fer is sensitive, terbium is sensitive. The demixing and mixing depending on electronic stopping power. Fer chrome mixing, like. Fer silicium, silicium insensitive, fer sensitive mixing. Srivastava. Nickel silicium mixing. None of them is sensitive to track formations. This is a big question. Palladium silicon, PATRA, just recently, also mixing, and none of them are sensitive. This is questions that allow us to say that there is some question mark in the observations of track formation that we have get previously. Is it the silicon or is it metallic? We have to understand that later on. And I think for a moment, we just make hypotheses. Now we can have interactions between nuclear and electronic and potential energy. I'm going to go through this. I still have 10 minutes, so I can do that. So you can have nuclear and electronic, whatever it is. You can have a combinations. Either it is negative, we can annihilate something, or it can be increasing the damage of the two, additive, synergy, or positive, we don't know. This is a question that we have between different combination of the two mechanisms. Iron. We have a very high electronic stopping power. This was done by Annie Dunlop. So I go back. I'm sorry, I don't know why, but I didn't see, I missed the slide. I'm very sorry, but I will show you that later on. So let us see. Titanium. This is tandem in Garching. This is what you have seen. And what we do observe, this is indium in indium on titanium, and we get something which is constant. gold and titanium, which is also something which is constant, while Sn is decreasing, Se is increasing, Sn is decreasing, Se. So why it is constant? Depending the fact that this is increasing, this is decreasing. This is the questions. We have something which is very surprising here. Starting SiO2, I go over because I don't have time. Amorphous SiO2. You have here the reference. We are in this regime where nuclear and electronic can be at the same order. This was done in Saclay. And this is we use the infrared. You can see the technique. Amorphous SiO2 on silicon amorphous SiO2. 100 nanometer, yes, of amorphous SiO2. And we measure the infrared transformation of this amorphous SiO2. And we can see that you have the increase of a new line, which corresponds to the change of the transformations of amorphous SiO2, and the decrease of the initial line of the infrared. And for this value of gold, and you can see, you get this, and you get the same evolutions. You can extract track radius, track cross-section from these two, peak area from these two. This is also one impact, and you get informations. And what we get for these two, we get a cross-sections which is around 50 nanometers square and 20 nanometers square. We have done several other experiments going from this to this, and never reach zero here. And if we combine that with the measurement of Sachs include, it's going back. So you have a kind of U evolution as a function of a beam energy. You never reach zero in track radius. Never, 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 when you use gold. And this is a question that we have to answer later on. And this clearly a synergy between the nuclear stopping power and the electronic stopping power, which is interesting. We will see that later on. Now, another thing which is also interesting, because this has allowed us to understand the material modifications by high charge ions at low velocity. This experiment was done in China by Wang, who tried to see, as a function of the beam energy, what is the beam energy between 0 and 5 MeV of gold, what is the threshold of potential energy needed to create a ELOC at the surface of the calcium fluoride. And you have all the other reference features here. So just to say to you, the potential energy, for example, this is 51 keV. It can reach with thorium very high, which is 200 keV, which is larger than any electronic stopping power that we can have. So this is to say that we can implement the potential energy, which is very large. And the problem is to understand what is this Spartan energy which is taken by the material and which is going outside. So we are in this regime, actually nuclear also, but electronic. But we are just dealing with a very low, very, very thin phenomena. So in low velocity, 2.2, 2.3, 3.6 keV per nanometers, you can see that you get a threshold with a potential energy which corresponds to the xenon 30 plus. And then you get ELOCs. So below 30 plus xenon, we don't have any ELOC formations on calcium fluoride. We go to this platform between 2 and 5 MeV, and we try to see what is the evolution of the threshold. 5 MeV xenon 21. 21 is very low as compared with the threshold of 28, but we have increased the electronic stopping power from 2.2 to from 0.1 to 2.2, but we don't see anything. I go to 5 MeV 22, we see a lot of ELOC. So there is a threshold between 21 and 22, which show that increasing the electronic energy loss, we decrease the potential energy to get ELOC. Here we go to 25, 26, but we are only at 3 MeV of xenon ions. SE equal 1.5 keV per liter. We decrease the electronic stopping power. We have to increase the potential energy from 20 to 26 to get the ELOC appearance at the surface of the calcium field. And if we look to the roughness, for 5 MeV, we get a threshold which is around 20. For 3 MeV, which is here, at this energy, there is nothing. So we can see that we have a combination of potential energy deposited inside the material and electronic stopping power. And this is what we have here. Here we have at 5 MeV, we use a potential energy which corresponds to this charge state. We see something, we see something, we see something, we see nothing. We see something here at 4 MeV. Here, 3 MeV, we see something. For 26, we see something. 25, we don't see. Here, we don't see anything. Here, we see something. Is nothing at very low velocity. So we have a direct line which going from the threshold of potential energy to the threshold of swift heavy ions, which has been measured and shown previously. So we have a direct relationship between potential energy and stopping power leading to that. This is very interesting because we can train the two phenomena to combine together. This allows us to go a bit further. And we can extract this following phenomena, that the depth in which the energy is deposited divided by the fraction of energy, which is potential energy, which is given, is a constant value, 4.2, which corresponds to the ratio of potential threshold to electronic stopping power threshold. So we have some constraint which could allow us perhaps to understand a bit better the combination of these two phenomena. Additive, but less than 2. So, in general conclusion of interactions may appear, I acknowledge all the different colleagues which are, and then I have finished. Thank you for your attention in the first part. If you want the PDF copy of my renewed presentations, you can write to me. Thank you very much. I am open to any questions. Hello?
Yes, sir. Thank you for such a wonderful elaborative talk about the thermal spike and tracks. So it is open for questions. So any students would like to have some query resolved? So already we have taken some of the queries in between when you stopped for the break. So maybe what can we do, Ashokan sir?
If you want
Sorry,
to take some rest, you can allow it.
Sorry, I was obliged to plug my computer.
Okay.
So could you repeat your question?
Yeah, if you want to take some rest, you can take a few minutes, then we can start.
When do you want that we start? Within how much time?
So maybe 15 minutes or so.
15. So this is to say, for me, this is 5:11.
Yes.
Yes? Okay.
Yeah.
So
you can take coffee and join.
Okay, I will join with a coffee. Yes.
Yes.
See you later. Bye-bye.
Bye.
Bye, sir. So all of you also please take some water and soothe your eyes not to look at the screen. And we'll be meeting after 15 minutes. So it is now 3:21, maybe around 35 we will be meeting. Okay.
Okay, Ashokan, so this is the gap which was supposed to be at 340, so we are a bit early, that means?
Sir, he actually left
He
some
was-
time for questions, 20 minutes.
Yeah, okay, so this is for that. ठीक है.
Yeah.
हमने कहा वो हम लोग program का timing I was just checking.
So
ठीक है.
after
all this timing all given by him. I have not changed anything.
ठीक है.
Okay.
Fine.
Okay.
all of you remain signed in, and maybe you can leave also because he has given the permission to enter, and join back after 15 minutes. Hello, sir. Marshall, sir.
Yes, hello.
Sir, your screen is being shared, so we can see
Okay.
your computer
Is it
monitor.
share? Is it share? Is it okay?
Yeah, it's fine with us. Means you wanted to do something, then you can remove the sharing option.
Okay. Yes, I understand what you mean. Doesn't matter. I was looking to some of it, the people who were here, looking the list of people. So,
Yes, I think you can start.
I can start.
Yes, yes.
So thank you very much for your attention. I think it's a bit heavy, but at least you get a PDF file of my presentation, and then you can go back. And now the second part, I call that a transient thermal process. This was long to pursue people to say that we can learn something with that. And I'm going to show that to you. And all this work was done in collaborations with two researchers from Caen, Eric Pommier and Christian Dufour. Eric Pommier is retired, Christian Dufour is still working. Ali Mefta from Algeria, Skida, and Ziguang Guang from Lanzhou in China. So, another time, this picture, we want to learn what is the material transformations under swift invariance, which is an electronic excitations. I repeat myself, look material transformation by femtosecond laser experiment, because you can learn a lot about that as compared to that. There is some differences, so you have to be careful not to apply directly that to that, but you can learn a lot. Just coming back, I have to understand the material sensitivity. Amorphous SiO2 more sensitive than indium phosphide, crystalline SiO2 more sensitive than indium phosphide, more sensitive than metallic materials. We have to understand that. Second thing, we have to understand the velocity effect, which is clear here, which is not so clear here because there is two beam energy and the same track size, and you see something. We have to understand that this velocity effect appear whatever is the material, all these references here. You have to understand amorphous material as compared to crystalline materials. Amorphous material is more sensitive than the crystalline one. And we have to understand the sputtering that appear at larger electronic stopping power than the track formation. And also that we have a radial morphology of a track, as an example in calcium fluoride, when you have a shell and a core. So all these things should be understood with the same idea. It's perhaps a bit optimistic, but we have to understand it. And then if we can explain the different phenomena, we can begin to see if this is interesting. And also to understand this, which is the non-zero track damage with gold MEV in amorphous SiO2. So in the different models that we have to our disposal, you have the time-dependent and kinetic Monte Carlo, molecular dynamic, accelerated molecular dynamic in order to get some more time, kinetic Monte Carlo, you have dislocation dynamic, phase field, and finite element and continuous equations. Our goal was to use this part, the finite element and continuous equations, in very low time scale. This was at the beginning one of the big breakthrough in the evolutions of the model in track formations, because nobody was saying this is too short in time and in space in order to apply continuous thermodynamics. There are some differences, but thermodynamics is something which is relatively good to be applied in this regime of nanometer scales and 10 to minus 13 seconds. The different track model, I think that Professor Srivastava has made a little descriptions. You have a Coulomb explosions when you create a charge state, and then the relaxation of this charge state create a damage. And this was proposed by these different things. The relaxation time is 10 to minus 13 seconds. A relatively recent experiment in 2008 show that these relaxations of electronic excitation is not in 10 to minus 13 seconds, then even shorter in 10 to minus 14 seconds, decreasing the efficiency of a Coulomb explosion. Then you get the thermal spike, which is when you have energy deposited on the electrons, an electron-photon coupling, local melting, and quenching. So this is a transient thermal process. This was proposed a long time ago by Sites et Colère in 1956, as you can see. And, sorry, 2 minutes. Sites et Colère, then Lichis, this was American, Lichis, which was Russians, which was during this time big competitions to have the atomic bomb. And then several times later on, in 1993, Dufour proposed something. And this is a macroscopic, because you do not take into account individual atom, you take a continuous system. Then you have microscopic, which is molecular dynamic calculations, and you can have ab initio lattice calculations. This is, you have to define an interatomic potential, which change for each materials. But the computer times is very large. And the first one was done by Urbasek. Later on, continuous electron subsystem was included as an energy input in the MD calculation. I will call the inelastic molecular dynamic calculations. And this was first done by Burr, then done by Kloot, and also done by Mukherjee in New Delhi. The inelastic thermal scale model is the one that I am going to describe, because it was for me the one which allow to understand a lot of different phenomena, and there is some also inconsistency that perhaps we can clear up later on by new experiments. So this was the first approach. This was a metal developed by Dufour, Wang, and then completed by Dufy in that time. In insulator, myself, Efta, and Avazou. In semiconductor, Kamaru and Schnorr, and then we have developed that by Sal. And interesting critical examinations, I encourage you to go to this paper, which is very interesting to understand what are the failures that we can have on the thermal spike. but also what are the interests of a thermal spike. What is a thermal spike? You have in materials two systems, an electronic system, and an atomic system. This is to say that you deposit the energy on the electrons, then the energy diffuse is deposited in a certain radius, then diffuse during a certain time on the electron, and then is transferred to the lattice, which create afterwards, if it is possible, a disorder. So I put that as an example for insulator. So you have a cylindrical system in which you deposit the electron in a time between 10 to minus 16, 10 to minus 13, and then you transfer the energy to a lattice, and then as a function of a radius, you calculate the heat conduction in the lattice subsystem in 10 to minus 13 seconds, 10 to minus 10 seconds. How can we do that? And this was another time due to an experiment which is done, I don't remember, but a French girl, which were a directrice of a CNRS in France, who tried to calculate what is the size of a sodium cluster in which you can have thermodynamic emission of atoms under femtosecond laser experiment. If a number of atoms is less than 10 of sodium, you have Coulomb explosions. If a number of atoms is larger than 20, which is very small, you have thermodynamic emissions. So this is to say that this is a very small, you can have an equilibrium temperature within 20, with a system of 20 atoms. So the inelastic thermal spike model or two-temperature model. Two-temperature model was used a long time ago for a femtosecond laser experiment, proposed also for ions. And we have an electronic equation, diffusion on electron, equation diffusion of atom, and the electron photon tilting. Specific heat for electrons, thermal conductivity for electrons, energy deposition on the electrons, coupling from the electrons to the atom. That's why it's minus and plus here. And then atomic specific heat, thermal conductivity. So all these parameters is known from measurement at equilibrium. And I must say to you that we shall use that, whatever it is. Now, initial energy distribution. And this is mainly due to the fact that we have to take into account that we can reach the same electronic stopping power for two different beam energy. As an example, 1 and 10 MeV per U for the xenon beam. The calculation was done by Katz-Kobetic here, Kobetic-Katz, Gervais and Bouffard, and this is the result of Gervais and Bouffard. When you are at low velocity, the initial energy distributions is given in this radius. When you are at high velocity, the mean energy is given in this radius. So you deposit at high energy the energy, the same energy, because this is the same electronic stopping power, in a larger volume than at low energy. And this is the phenomena that you should have in mind, whatever it is. When you are at low velocity, the energy is more concentrated on the electrons than at high velocity. We calculate some MD calculation was performed in order to see what is the distribution of energy on the electron as a function of the beam energy. This is the ion, this is the relative velocity as compared to the light velocity, 0.2 to 0.99. You can see that the center, the dose, the energy, which is the dose, is decreasing and distributed on a larger volume. And what we have done, we have made calculations using Valigorsky in order to calculate what is the energy fractions in a cylinder radius. For this free energy, and this is a cylinder radius, we can calculate that from Valiogorski for 0.1 MeV, 2 MeV, and we get 0.6 nanometer, 3 nanometer, 10 nanometer for 66% of energy which is deposited in the lattice. Going from 0.6 to 10 nanometer, as it is a radius, if we go to surface, there is 2 orders of magnitude change in energy density. That's why also you should have some change in the track sensitivity. And I plot here the mean absorption radius, in which 66% is deposited in different materials. And you can see that depending on the density of the materials, you have different radius in which the energy is deposited. Lower is the density, larger will be the radius as compared to high density. For example, here for uranium oxide, this is 1.5, while for SiO2, this is 3. No, this is, yes, 1.5. This is a factor of 2, which is a factor of 4 in the energy density. So uranium oxide should be more sensitive than the silicon oxide. All these phenomena has to be taken into account in any descriptions by the energy deposited on the electron. We know that the initial energy deposition is well known, and this is the interest of the swift heavy ions, because we don't have, as compared to femtosecond laser experiment, energy dissipations by electron emission at the surface. And no reflectivity also, because when you have a light on the materials, you have reflectivity, and the difficulty is to know what is the variation of reflectivity as a function of the number of excited electrons. So the interest of the swift heavy ions, we know what is the energy deposited inside the material, and this is a big interest of swift heavy ion. This 2 temperature model is a bit complicated to solve, because this change as a function of the temperature, this change as a function of the temperature, this also changes as a function of the temperature, this and this. All is changing as a function of the temperature. So we cannot solve that without any numerical solutions, which has been described here by Christian Dufour in this paper in 1942. And you have a numerical solutions for cylindrical geometry for track formations. And this numerical solution was used in the code in order to describe the evolution of the temperature as a function of the time for electron and for atoms. I skip this part of electronic temperature because you can measure that by Auger spectroscopy. You have these 2 references. See this quoted reference. This is a bit interesting because we see that we have some touch about the electronic temperature, but there is some difficulty to understand the difference that they do observe. There is large temperature with Chivitz, relatively low temperature with Caron, but it can be interesting to look at that if you want to go further in the electronic temperature. But I will skip, I don't have time. Atomic temperature. In order to have something which is consistent for all the different materials, we are obliged to be very strict in the definitions of the parameter. And that's why I say initial conditions for the lattice parameter. First of all, lattice specificate. We have an evolutions of a lattice specificate, which has been measured as a function of temperature, and you have some very well defined. Lattice thermal conductivity also. You can measure it, and you have some measurement in different materials. And these 2 are given by the literature, and you stick on that. You have some uncertainties, but you will, if you make some calculations and you work on that, you will see what is the sensitivity of each material as a function of the different value. Thermal conductivity is less sensitive than the specific. Now, melting temperature is not a good criteria. This is a question that is still under discussion. You can see some calculation which is done stopping the temperature, the melting temperature. But you should look this paper, Hermes et al. Applied Physics in 1986. We do try to measure the temperature by particle emission under nanosecond, picosecond, and nanosecond laser pulse. And what they see, very surprisingly, when you do irradiate a metal with femtosecond laser pulse, the temperature, you measure the distribution of atom emissions using a Boltzmann distributions, and by this measurement, you can see with femtosecond laser experiment, you never stop at the melting temperature. You surpass the melting temperature in order to reach a kind of small plateau, and then you go to melt phase. This is to say that melting temperature is not a good criteria. You cannot, due to the very short excitation time, you don't stop to the plateau due to the melting temperature. This is just due to the fact that atoms don't have time to move in the time of energy deposition. This is to say that you still have the same compact phase. So we need to change the criteria to get a melt phase, and we use the superheating scenario, and which define an energy necessary to melt, which is the energy to reach the melting temperature, plus the relative of fusions in order to go from solid to liquid phase. But this is the energy to define a melt phase. Same thing for vaporizations, vaporization temperature plus latent heat evaporation. And this is taken from experimental measurements. We do not change anything of the parameter. We use always the same. And this is important just to say, to stick to these definitions. Then afterwards, you will be able to compare what is going on. As an example, I'm going to go through the different parameters for iron, internal energy for melting the irons. The lattice specific heat as a function, we integrate that from 0 to T0. If T0 is 300 K, the initial energy is 0.065 eV per atom. You calculate that just by integrations. Now, if you go to the melting energy, you reach the melting temperature by increasing the energy to this value. You add the latent heat, you arrive to such melt energy, which is 0.92 eV per atom. Now, at this energy, the energy to melt is, at this temperature, the energy to melt is this. Now, if you go to this energy, the superheating temperature is 2200 K. So you increase the temperature by 400 K due to the superheating scenario, which is due to the fact that you deposit the energy in a very short time. Now we go to metals. The electron energy diffusion for metals is the following. We use a quasi-free electron gas model using the gold as a metal. We are going so quickly in energy depositions that the electron energy is going directly to the Fermi energy, a very high energy, and forget what is the structure of the materials. And so the specific heat as a function of electronic temperature is going like this. The thermal diffusivity is going like this from very low temperature, this with a minimum value, which is around 2 centimeters square per second, which is limited by the fact the interatomic distances limit collisions between two electrons. Taking into account the velocity of electron and the interatomic distances, you will be able to calculate that the minimum diffusivity is 2 centimeters square per second. And this is shown clearly by Martinenko and Yavlinsky. Electron-phonon coupling, and this was proposed by Kaganov and by Allen. And the electron-phonon coupling is proportional, so this is constant Boltzmann number of electrons, velocity of a sound, and electronic thermal conductivity. This electronic thermal conductivity will be the measured thermal conductivity as a temperature Th. Because in that case, and we use that, we define that always like this, in order, because the thermal conductivity in a metallic system is due to the electron conductivity only. So we have something which is like this. And then we can define an electron-phonon coupling with this number of electrons. If we use a measure thermal conductivity, the electron-phonon mean-free path, which is like this, and the electron-phonon mean-free time, which is like this. And here you have the thermal conductivity as a function of the temperature, and the electron-phonon coupling, which is increasing if you increase the temperature of the atomic system. And we understand that very easily due to the fact if you increase the temperature of atomic system, the vibration of atom increase the cross sections when an electron can interact in between. So this is what you have here. Now for different metallic system, so this is the electron-phonon coupling. This is inversely proportional to the atomic thermal conductivity of materials or electronic resistivity of a material, proportion or inversely. And you get for copper, bismuth, iron, titanium, and graphite, a variation of electron-phonon coupling by nearly a factor of 300. So this material is very sensitive as compared to copper. Copper is not sensitive. And then you get the electron-phonon mean-free path, which is nearly 10 to minus 12, going to 10 to minus 13, and going to 10 to minus 14. So you get 2 orders of magnitude change in the electron-phonon mean-free time, and the electron-phonon mean-free path is going from 1 to 13 to 1. This is to say that the energy on the electrons is moving on the electron on 10 nanometer for copper, 10 nanometer, while only 1 nanometer in graphite. And this is to say that you will concentrate the energy on the electron in a very small volume as compared to copper. Now, this is the crude result of the calculations. What do we calculate? We calculate the evolution of the electronic temperature as a function of the time for this condition, 17 keV per nanometer for MeV in irons. We use the electronic stopping power, which is due to that, and we use the energy distribution calculated by Vardiovsky. And we arrive to the evolution of the temperature as a function of a different radius from the center to 9 nanometer. And we can see that we increase directly in the center, and then the energy is diffusing on the different radius, and then going back nearly to room temperature in a time of 10 to minus 12 seconds. In this time of 10 to minus 12 seconds, you can see that the atomic temperature in the superheating scenario is increasing to a maximum around 10 to minus 12 seconds. So you can see that you have a direct transfer of energy from electron to the lattice here for different radius here. And this temperature can be transformed in EV per atom, which is the same definition than the temperature, but in a superheating scenario, it's difficult to plot that, because people will say, "Oh, the temperature melting is here. Why you don't melt 5 and not 4?" melting criterion is more complicated in superheating. That's why I prefer to use the EV per atom, which is 0.9 EV per atom in irons, and you get a radius which is around 4 nanometer melt phase. The second thing which is important is to say that the high temperature stay only 10 to minus 12 seconds in the metallic system. Try to remember that later on. This is that. I go further. In iron, you get a number of defects which is decreasing till here when there is a threshold of track formation, and then increasing drastically. So this is track formations. This is a kind of defect annealing. Can we describe this defect annealing? And we will work on that more precisely. First of all, this is the number of defects which has been measured. And if we use binary collision theory, we have a number of defects which is going like this, increasing instead of decreasing. Why? Can we understand that? So if we go to 25 keV per nanometer, we are below, we can calculate what is the evolution of the temperature as a function of the time for different radius. With this electron-photon coupling, this is a theoretical one, this is the one that we are used for the calculations. Can we describe this decreasing? And we use the probability to anneal a defect using this probability. When you have the activation energy to anneal a defect, the probability to anneal defect, and then the temperature of the lattice. This was done by Wang et al. By determining the energy, the distribution of defect around the track. And what we measure, what we calculate is the following. If we introduce some number of defects which are around 5.5, which is between 5 and 6, and we apply this model of probability of defect annealing, we get a number which is this one. So we see by the thermal effect due to the electron temperature and transfer of energy of electron to lattice, which is the lattice temperature, we can anneal defect. He has calculated the evolutions of a number of defects annealed as a function of the electronic stopping power, and we observe something which is exactly decreasing as we do expect. The surprising thing was multiply this by around 0.5, we arrive to something which is exactly in this evolution. This factor of 0.5 approximately is something that we have expect when we are in the nuclear collision regime. The number of defects which is created is often divided by 2 in order to have a number of defects which is really observed. So we get something which is very interesting because we can simulate the defect creation in this defect annealing in irons. If we go a bit further, this is the thing, and we calculate what is the maximum temperature for each value of electronic stopping power, and we increase to 50 keV per nanometer, and we get a temperature, a maximum temperature of 2200 K, which correspond to the superheating melting temperature as we have calculated previously. So this support another time that the superheating melting temperature is a good criteria to define a track formations because the track appear here. So I come back to this picture another time. When you have the electronic temperature as a function of the time, the temperature atomic temperature as a function of the time and the deposited energy as a function of the time, and we arrive to the same value, whatever it is, temperature or EV per atom, and we melt around 4 nanometer for this case. And if we compare to the track size as determined by Annie Dunlop, we arrive to the fact that we have something which is around this in these cases. 70, you get 4 nanometer. This is exactly what do we expect with 5 MeV per year. So this description support that melt phase can be the criteria to create a track in a metallic material. And this is important because this was not an hypothesis. We can describe the annealing of defect, which is quite well known. And by this annealing of defect, we can extrapolate that the melt phase is a good criteria to create a track inside the material. Now, if I concentrate on this part, another time, we have here, and if I calculate the energy, the radius of track, just to reach a melting temperature, I get something like this. If I use the energy to melt, I get this. Another time, this is clearly the superheating scenario, which help us to describe the track size. And we see the velocity effect, which is due to the fact that initial energy distributions is narrower here than here. Titanium, the G factor which has been fitted the track is 1 by a factor of 2 larger than the theoretical one, but not too far away. Oh, I make a mistake here, this is 0.9 also, but that's it. And if I go to amorphous iron boron, we arrive that we need to have an electron-phone coupling of 5×10 to 12 as compared to 1.2 but theoretical is not easy to determine. But if we know that the resistivity in an amorphous material is larger than in a crystalline materials, it is expected that we get a larger electron-phonon coupling in an amorphous material as compared than crystalline materials. And that's why we can, with this explanation, to say that resistivity is a good tool to see that we are more sensitive or less sensitive in a metallic material is a good criteria. Bismuth. Bismuth is a bit complicated because you can see that it has a very large track and it should be perhaps larger than iron and larger than the electron-phonon coupling, but not. If we, first of all, the energy to melt is 0.26 as compared to 0.9. This is by a factor of 3 smaller. And if we use the thermal diffusivity that we use at room temperature for a metallic system going to 2 centimeters square, we arrive to this evolution, which is far away from the evolutions of the track size. And from the theory, this is that. So we are not far away, that's clear, but it's not as good as it could be. And we decide to change the maximum, the electronic diffusivity at room temperature because radius, bismuth is a semi-metal, sorry. Bismuth is a semi-metal. And this was explained in this. And you can see that using this parameter, we are able to fit all the track size in the bismuth. And the larger track is due to the fact that the energy to melt is very low, first of all. Secondly, the electron-phonon coupling is very low. This is to say that the expansion of the energy on the electronic system is larger than iron and titanium, for which the electron phonon is very large. So going very quickly to the lattice is going very small, very long time before going. Sorry, and if we do the same calculations for the evolution of the temperature, this is for two different electronic stopping power, 31 and 37. 31, we get something which is like this, 37. So we see a very big evolutions of the track size. This was the previous one calculation, does not. So we have been able to describe the bismuth and the metallic system in using the thermal spike model. And the conclusion that we can take from the metallic system is that melting energy, taking into account the energy to reach the melting temperature plus the latent heat, is a good criteria for track formation. Now, if we go to insulator, the difficulty is linked to the fact that there is no free electron. But what we can imagine is the following hypothesis. We excite electrons from the valence band to the conduction band. And when the electrons are in the conduction band, then they are at high energy, at high temperature. And when electrons are at high temperature, the thermal diffusivity is the minimum one that we can have, and the specific heat is something which is around this value. So we have decided for the insulators that the electronic system will behave with such a value of electronic diffusivity and thermal, donc consequently thermal diffusivity and specific heat. Then the electron phonon coupling is linked to that. This is to say, this is 2 over lambda square, and lambda, which is the electron phonon mean free path, will be the free parameters in order to quantify the track size, assuming another time that melt phase is a good criteria, energy to melt, which is plus melting temperature plus latent heat. This is another time the real crude result of a calculation at the electronic temperature as a function of a time, atomic temperature, deposited energy in EV per atom. And you can see that in a time of 10 to minus 13 seconds, you get the maximum temperature in the lattice. This is the same in energy deposited. But the other interesting thing is that the time of cooling is 3 10 to minus 11. This is 30 times larger than the metallic system. 30 times larger. So the cooling time in an insulator is very low because there is no electron to transfer to conduct the energy. This is by the atomic system. Now we have to determine the lambda. Another time for lithium niobate, we calculate the energy to reach a melting temperature. This is 0.3. The latent heat is 0.40, and this is the energy to melt. But you can extract from this curve when you have a specific heat as a function of the temperature. If you integrate this energy in joule per gram, you get this curve. And if you transfer this joule per gram in EV per atom, you get this curve. And you arrive to the fact that 0.57 corresponds to 2000 K, which is a larger temperature than the melting temperature. So we use that. And then we change the electron phonon coupling by 4.3 and 7. And this is very sensitive here in this low energy regime, very sensitive. And you can see that 4.3 nanometer is the best value of electron phonon coupling, mean free path, electron phonon mean free path, in order to describe the track. Here, the error is too large in order to apply this. So we have done that. And, and we calculate a band gap and the lambda. And we do like this. You have 4 different barium, get a lot of different material. This is plotted here. You have a band gap, you have a lambda, and you see that the lambda is decreasing as a function of a band gap. How can we understand that? And then I will think, how can we understand that? When we excite electrons, the electrons cool down by exciting electron from the valence, cold electron from the valence band to the conduction band. Lower is the back, is a band gap. Easy will be to cool down the electrons by exciting the electron from the band gap to the conduction band. This is normal. If you run 1 EV to transfer energy, it will be easy to transfer 1 EV as compared to 10 EV. And that's why the difficulty for the energy to expand in the materials is increasing when the band gap is increasing. Metallic system, the G factor is going from this. In insulator, this is 2 over lambda square, and this is 10 to minus 13, 10 to minus 14. So insulator has a G factor which is larger than the metallic system. As expected from Kittel, the electron phone coupling is weak for semiconductor, intermediate for this one, and strong for this one. And very strong for amorphous material. So now if we go to SiO2, you have the energy to melt. We try to feed this data with the best value of electron phone coupling, 3.8 nanometer, and we get this evolution of the track size. Now I go to the sputtering. The sputtering is a statistical determinations, which is linked to the sublimation energy and the temperature of the lattice. And then you have, as a function of the temperature and evolutions of a rate, and the total sputtering rate is the integration over time and over the radius of this value. And you get 2 important parameters, the sublimation energy and the time. And if I use that to calculate the sputtering rate of SiO2, this is the electron phone coupling, the energy to melt, the energy to sublimate at 1 MeV per U, and we get a sputtering rate which is around that, which is not too far away from what we do expect. So we can see that we have a relatively large sputtering rate in crystalline SiO2 in this regime. So I stop here for 5 minutes. Yes, I stop here for 5 minutes. If somebody wishes to ask questions, I'm ready to answer. Hello?
Yes,
Hello?
Yes, we are there.
Is there some questions to go through? Will I go through?
I could not see anything in the chat box.
No, I have to. So,
I think you
if there is no more question,
yeah,
I think
you
I
can
will
continue. Yeah,
I will continue. I will continue. So now I go through core shell structure of track in calcium fluoride. We see that we have a core shell in amorphous SiO2. We are also in core shell in calcium fluoride. And what do? From this curve, we get the electron phonon mean free path for calcium fluoride because the gap of the calcium fluoride is around 12 eV. Okay. Now, I use the energy to melt the energy to vaporize, and I define, and I try to see what is the radius in which the male phase appear, and what is the radius in which the energy to vaporize appear. And I arrive to these two curves. And the surprising thing is that I can correlate the core track to vaporization in the track of the calcium fluoride and the shell track to the melt phase. And this was my surprise that we get and that we have explained in this paper. So we can have a track which is linked to the vaporizations, and TEM, which appear only and tracked by TEM, is observed only when we are above the vaporization track, and we cannot see track in the shell track. So this is the same if you remember the cerium oxide, when there is two balls and a very small track in between the two balls. This is exactly the same. This is to say that the disorder that we can see in ionic crystal is only due to vaporizations, but we cannot see the disorder due to the melt phase in an ionic crystal. This is one of the problems that we have to understand those things. If we go to yttrium ion garnet now, I want to show you what is going on for the velocity effect. And the electron phonon mean-free path is 5 nanometers. And over time, we get this. We get the evolutions of the alpha R as a function of the beam energy, which is the radius in which the energy is deposited on the electrons. I repeat, on the electrons. And you can see that is evolving from approximately, this is 1 here, 1.5 to 8 to 9 here as a function of the beam energy. The electron phonon coupling is 8, which correspond to the same, to 7 MeV, to the same radius of the energy on the electron at 8 MeV per U. Now I go here. This is 0.5 MeV per U. We have such kind of energy distribution on the electrons, and you have the electron phonon coupling, which is here. The energy is diffusing from this size to this size before going to the lattice. So this is to say that the initial energy distribution is very small as compared to the electron phonon coupling. We can think that the electron phonon coupling will define the volume in which the energy is deposited on the atom. I go a bit further to 1 MeV. Another time it is 2.5 as compared to 5. Another time, which is smaller as compared to the electron phonon coupling. And that's why we see the same track size, because this is mainly the volume in which the electron phonon coupling will deposit the energy, which govern the energy distribution on the atom. And now, if I go to 15, now we are above, and we have a combination of electron phonon coupling and the initial energy distributions. In order to express that in another way, I define a radius atomic in which the energy is deposited, which is the square root of the electron phonon coupling, which is a constant, plus the energy distribution on the electrons. And I plot that here in red, which is here, as compared to the initial energy distributions. And you can see that for 0.5 and 1 MeV, the variation is negligible between this for S square. This is to say that we get approximately the same radius, but if we go here, you begin to have big differences as compared, and that's why the track radius is decreasing. So the velocity effect is something which is not easy to handle immediately. Not easy to handle. As an example, but I cannot plot that, but if it was 2.5 nanometer of electron phonon coupling, we should have a big change between 0.5 and 1 MeV. And this is depend of the electron-proton coupling, of the energy distribution in the lattice, which is not the same for the same materials. So that's make the things a bit complicated, but you can have some idea by making some calculation with Vygotsky and comparing to the electron-proton coupling, and to see in which regime you will appear to have some result. Another time, core shell and sputtering in amorphous SiO2. So you get the core track as a function of beam energy, the shell track as a function of beam energy, and here this is the energy to reach the vapor phase as a function of the radius to reach the vapor phase, and the radius to reach the melt phase as a function of a beam energy. And we are not too far away to another time to say that the core shell could be the vaporization, and the core could be vaporization, and the shell could be melt phase. Now, in this case, you have an underdense core and overdense shell. When you arrive to vaporizations, the vaporizations want to expand. If you want to expand, it will decrease the density in the core and will push melt phase to reach an overdense shell. And this can explain that we get the underdense and overdense core and shell. This is paper of Kloot, I don't know. No, it is, the reference is here, sorry. But this is exactly what we should have. And when we make different calculation from the case of Kloot, we get here the thermal spike model, the core stem and the core shell core sacs, and then the shell. We get something which is in good agreement for this energy to melt, this electron-proton coupling, which is 2.5, and this energy to vaporize. But does this energy to vaporize allow us to describe later on the sputtering? But if we have MD calculations, this is the MD calculations, which is a number, which is the normalized density as a function of a distance from the track centers. And MD calculations show clearly when you are at very high electronic stopping power, this point, you have a very low density, this is to say nearly a hole inside the SiO2, and you get an overdense shell here. So this is also confirming that we get underdense and overdense core shell. And when we look to infrared, we can get a track which is here. We cannot see in the core because there is nothing in the core. Infrared is linked to the SiO link. If there is no SiO link inside, we cannot see it. And we're using the sublimation energy, uranium and that, we get these evolutions of a sputtering rate. You look this paper with a reference in the quote paper, which is for this black point. This is not our result, but we get something which is the evolutions with that. So with these two values, energy to melt, sublimation energy, or energy to vaporize, we can describe the shell, we can describe the core, we can describe the sputtering rate. So this allows us, with all these parameters, to describe 3 different phenomena in amorphous SiO2. This also helps us to understand that thermal spike model could be a good tool to understand track formation, despite the fact that we don't see everything in the material, like in calcium fluoride, TEM, see only the core. So we have to be careful when we make comparisons, but transient thermal process within this hypothesis is a good tool to understand how the thing is going on. Cluster embedded in vitreous SiO2. This is you have a cluster of 18 nanometer, which is irradiated by 74 MeV krypton, and you can see that a cluster of 18 nanometer diameter elongate, 24 nanometer elongate, 40 nanometer begin to be difficult to elongate, but you get kind of things. And then here, nearly you don't elongate. This is to say that a cluster which is a diameter of 75 nanometer is not sensitive. It is a cluster of gold. Gold is not, we know that gold is not sensitive. So we come back to the non-sensitivity of a gold when the cluster is a diameter of 75 nanometer or larger. So we come back to what we know. But you can see that cluster could be very sensitive to that. And this is due to the fact that at the interface of a cluster, the electron cannot escape due to the interface. And conclusions, you arrive to situations that you can, the energy is concentrated in the cluster and cannot go in SiO2. This is the idea before any calculations, which has been done later on by Dufour. Just forget to say here that this experiment was previously shown by d'Orléans et al. In Strasbourg on a cobalt cluster in amorphous SiO2. This is a calculation of a temperature. What is the molten fractions as a function of a time for a specific cluster size in which you can melt completely. So here, this is the electronic temperature. Here, this is the lattice temperature. You can see that the electronic temperature in a small cluster size is very large and stay in the cluster and has some difficulty to go inside the SiO2. You begin to expand the energy on the electrons after this time to expand a bit more, and then it's cooled down. Here, this is the atomic system. The atomic system is still solid. Then you begin to increase the temperature on the shell because the electron energy is stopped there and then go back afterward inside. So you begin to melt the cluster in a circle along near the surface, and then it's go inside, and then after it go down. So this is the interesting things that interface play an inhibitor of energy diffusion on the electrons, and that's allowed to confine the energy inside the cluster and begin to melt at the interface. That's why you see here at the interface something which is a bit changing in size, because you can melt the surface, and the surface is going like this, going in the track size of the amorphous SiO2, because the track size does exist, whatever it is, so it's going in track size. So here you vaporized. If a cluster is smaller than 10 nanometer, they disappear completely, and the cluster vaporize inside the SiO2. Now between 10 and 35 nanometer, the cluster is completely molten. Then when you go from this to this, you see a decrease of a molten part of the material which is molten, but molten near the surface and decreasing, and here there is nothing. So another time we arrive to the same result. A cluster with a size diameter less than 80 nanometer cannot melt. This is important if you do irradiate a cluster, because this is to say that the size of a cluster can allow you to have a melt phase or not, if a material is not sensitive, or to change the property of the energy which is deposited inside if you have an interface. So you have to have that in mind. A surface of a cluster is a kind of inhibitor to transfer the energy far away. Now, if I go to the sputtering, I just want to point several things. First thing, at high temperature, insulators stay free 10 to minus 11 seconds, metals 10 to minus 12. So there is 30 times larger for an insulator. Sublimation energy in an insulator is often smaller than metallic system. These two phenomena is going in the directions that an insulator should be, the sputtering of an insulator should be clearly larger than in a metallic system. And we see that immediately. Titanium, zirconium, SiO2 is a large order of magnitude. The problem gold and titanium, we don't understand because gold is not sensitive, titanium is sensitive, but there is more sputtering rate. Perhaps nuclear collision play a role, we will see. Amorphous carbon by CAN is like this. Now, if I go to the thermal spike model, sputtering rate for ICO2, CaCO2 insulators, we can describe by the thermal spike model. For calcium fluoride, lithium fluoride, we cannot describe by the thermal spike model. We cannot, we do not understand why there is a so large sputtering rate in these materials. For gold, titanium, and zirconium, you have a combination of elastic, which is the nuclear collision regime, and inelastic thermal spike model. So this is to say that we have some differences between all the different phenomena. And if we can explain the metallic system by a combination of elastic and inelastic, we cannot explain this part of the silicon. This is one of the open questions in the energy depositions inside ionic crystal. If I go now to semiconductor, I go to the paper of Sal, and this is track radius as a function of electronic energy loss. The bond gap is this, lambda is 4.7, and I can feed the track in gallium nitride. If I go to aluminum nitride, for which the gap is 6 eV, a lambda which is smaller, then we get that for the mel phase, and we cannot feed the track, which is here. It seems to be 8 nanometer. So here we can use the lambda versus band gap in order to describe the gallium nitride. Here we cannot. Why? If we do the same thing for germanium as in silicon, we get a lambda value which is larger than the one which is described by the insulators. We get some case which correspond to the band gap, the curve given by insulator. There is some case which is out of the insulator, and even more. As an example, indium phosphide, which is a 3,5 compound, as compared to gallium arsenide, which is also a 3,5 compound, we see big differences. So this is an open question mark for the thermal spike. As I say, it's lambda 7, 15, 6, 13, why? This is the same gap, approximately. Question mark. I want just to give you something regarding tumor therapy, because this is important to use carbon-12 ions in order to get some therapy of a cancer, which is the hadron therapy. So you know that we are using very high energy. We sweep the beam in order to get to kill the tumor which is here, and we also change the energy in order to change the range of the particle. And this is the dose distribution a function of a beam. And if we change the beam energy, we arrive to something which is a relatively biologic effectiveness, which is like this. This is one way to understand Is it true? Is it not true? And this picture are given by Christina Trotman. But when I calculate what is the maximum temperature as a function of different lambda value in water as a substitute of biological materials, I get something which is like this. This is 300 K. This is 373 K, which is the energy to melt. And then we have to set 7 kV, 1000 kV. Sorry. This is to say, this is at 5 MeV carbon, which is very easy to produce in any accelerators. And you can have a very large temperature inside the water. You vaporize the water. If you vaporize the water, this is the temperature, you calculate the pressure, you have a very big pressure. This is to say that in the core track, you vaporize, you create a shock wave inside the materials, and this shock wave can kill the cancer molecule. This is a question mark. Nobody has made any proper calculations to see if this pressure can help in the hadron therapy. But we know that the shock wave, whatever from the fireman or from the military bomb, we know that the shock wave can kill a people, and we don't see that. We kill all the molecules. So it could be interesting if somebody wants to work on that, and I can add them in order to have better value of the lambda electron photon coupling, to see does the pressure which is induced by the increase of temperature and the shock wave which is initiated can kill cancer molecule. So now I want to talk about the interaction between nuclear and electronic and potential energy distributions to see how we can have interactions between the different processes of energy deposition inside the materials. Before that I go inside this, does somebody want to have a question or not?
So there is a one in the chat box.
Can you look at the chat box and give me the question, please?
It is the C carbon, I suppose, will then also damage healthy tissues before reaching the cancer, before reaching, this is what is happening. Carbon also damages healthy tissues before reaching the tumorous cell.
No, the interest of the carbon 12 is due to the fact that the maximum energy, I come back here, maximum energy is given in the black peak. This part of energy disposition is very low as compared to the black peak. And as compared to X-ray, which is something like this, the damage that we can create on near the surface and just before the tumor is very small as compared to X-ray therapy for the cancer. So this is to say that all the phenomena appear here. Secondly, the shock wave will be given in a very small, a larger volume than the vapor phase, but in a very small volume, because the shock wave will decrease due to the fact that we increase the volume in a cylindrical way, in which the energy is deposited. So we will not destroy a lot of molecules around that.
Okay. So one query I am having, actually these shock waves are appearing for only very small period of time, 10 to the power 16, 17, yes. Minus 16, minus 17.
10 to minus 13 seconds.
13 seconds. So is this time sufficient enough to kill the tumorous cells? Or we have to repeatedly do it one after the other, sequential?
No, I was surprised when I was hearing people talking about the fluence needed to use in cancer therapy. And I says, let us see if a track size in water could be explained that. But if I use the track size in water, this is a very large fluence as compared to what they use in order to make a therapy. So my feeling is that the track size water is not enough. We need to have something which expands along the track size. And I was thinking that the shock wave could increase as compared, like an atomic bomb. We see the atomic bomb in a very specific place, but we see the shock wave which is appearing on a long distance. So not so long, but on a larger distance than the initial energy deposition. This is the only thing that I can say. I just say that because nobody has made any calculations. This could be difficult because we need to know somebody which is able to make calculation in hydrodynamic, but could be very interesting, perhaps, to understand the hadron therapy. And we will have an answer, yes or no, because we have a calculation, if it is possible to do it. We need to know somebody who is doing some shockwave calculation, like the shockwave that we have for the sound in when a plane is going above the velocity of a sound. This is something like this.
Okay. So one more student is asking, as you have shown, there is no elongation of gold embedded cluster when the cluster size is below 10 nanometer. So we can say comparable to track size, or we can say comparable to track size. So below 10 nanometer cluster size region, what changes we could expect?
Then this is we vaporize the materials. So in this case, the gold is distributed in SiO2, and as the SiO2 does not allow the gold to be stable inside, is moving till he found another cluster. So you can increase the diameter of elongated bands. So now if you have vaporizations, you go to other cluster which is around. So this is you can increase the size of a cluster, and after the cluster is stabilized on a certain size.
Right. So these are the questions.
Thank you. So I will continue now on the interaction.
Yeah.
So interactions, first of all, another time, we have this curve, which allows to say that we can have mixing of a different energy deposition, nuclear and energy. So I go to iron, defect annealing on iron. As I already discussed, and I say that another time we arrive to a situations that we anneal defect inside irons. This is a competitive interactions. One is a nuclear defect. One is the electronic annealing, and we get something which is smaller than one. So we are in a competitive interactions. This was explained previously. And as I say to you, this was a very good insight to say that the superheating melting temperature could be a good criteria to define the track size in the materials. Now, sputtering of gold in nuclear energy loss. This is surprising because we are in this energy, very low, you can see. And this is a measurement which has been done by Anderson and Toll when gold is irradiated by gold ion between this 20 kV to 2000 kV, 3000, and we get such kind of evolution of a spectrum field. And we decide to use the elastic collision spike as proposed by Sigmund to calculate the sputtering rate, because we know that gold is not sensitive. So if it is not sensitive, this is a collisions, elastic collision, we should propose a sputtering rate. So we define an energy distribution, Here, this is the energy distribution due to nuclear collisions. We integrate to have electronic stopping power. We use another time the sputtering rate and the total sputtering rate, as this has been done previously. And we calculate the sputtering rate by elastic collisions. And we arrive to something which is by a factor of 2 or 3 larger than the measurement. The elastic collision spike seems to increase the sputtering rate. But then we decide to say, okay, but we have electron in the gold, and we can transfer energy from the atomic system to the electronic system. Does the electronic system can cool down more rapidly the atomic system? Within 10 to minus 13, atomic temperature is larger than the electronic temperature. So you transfer energy from the lattice, from the atom, to the electrons. By doing this calculation and using the known value of electron-photon coupling, we arrive to the evolution of the electronic temperature and atomic temperature as a function of the time. We can see that we deposit some energy on the electrons due to the electronic stopping power, but we don't transfer the energy. But when we arrive here, when the atomic temperature is relatively large, you transfer energy from the lattice to the electron, and you get electron temperature in a range when it was not expected previously when we do. So we arrive to this, and then when we calculate the sputtering rate, taking into account that the atomic system is cooled down by the electronic subsystem, we arrive to fit the evolution of the sputtering rate. Surprisingly, we were surprised to see that we say stop. So somebody should perhaps redo all this calculation in order to be sure, but at least it is expected that we get an electron-photon coupling who cool down the atomic subsystem, and this was previously proposed by Averbach when he was explaining that in nickel there is more defect staying after nuclear collision than in copper, because the copper the electron-photon coupling is smaller as compared to nickel, and so it can cool down longer time than the nickel. So cooling, it's a competitive interactions. Titanium. So I remember to you that it was nearly constant. So we repeat exactly the same calculation than for gold. First of all, we calculate the sputtering rate by the electronic stopping power. We arrive to something which is like this, very low as compared to the experiment. We do the same in the elastic collision spike. We get something like this. If we sum this and this, we arrive to this. So this is not the sum of the sputtering rate of independently of electron and nuclear that can suggest that there is a large sputtering rate. Now, if we do the same, if we make complete calculations with increasing the temperature of the lattice, increasing the temperature by the electronic subsystem, we have something which is like this, which is slowly decreasing as we do expect from the experiment, and we increase significantly. This is a kind of synergy between the two, and this is due to the fact that the sputtering rate is directly linked to an exponential, and when you increase the temperature, you increase significantly the sputtering rate. So synergetic interaction, 1 + 1 is larger than 2. Amorphous SiO2. So we want to explain that. Another time we repeat the same calculations, but we have to be careful, because in this regime, and this was said by Srivastava in the morning for you, the Electronic stopping power in this regime is not well described by stream. And this was proposed by Sigmund, the calculation, and there is an experiment by Zhang et al. In Journal of Applied Physics in 2009, showing clearly that the calculation given by Sigmund is better than the one by stream. I skip the stream because the stream is something which is here. So electronic stopping power at low energy has to be very carefully determined, and you should be very careful when you go. But this is interesting because you have interaction between nuclear and electronic. Now, if I calculate what is the energy to melt, this SiO2, I get this is something with electronic stopping power, which is the shell from Clout et al. If I go to just elastic collisions, the number of atoms which is in which you have something which is very small. If you use the elastic collision spike as Sigmund in 2000, using these equations with an initial energy distribution in, you arrive to these evolutions of a track radius. So you arrive like this. And if you make a combination of the two at the same times, electronic excitations, atomic excitations, you make a two, then you arrive to something which is like this, which allow to describe the U curve of a track radius, electronic plus nuclear. It seems to be additive, nearly additive. And this additivity, which is the conclusions, was shown also by molecular dynamic simulations by Bachmann et al., who determined recoil spectra in MD calculation. And then after, we superimpose a thermal spike after 100 femtoseconds, and we can compare the defect created by recoil, the defect created by thermal spike, and the defect created by a combination of the two. And we arrive to the result here, the number of defects per atom as a function of the beam energy. This is for nuclear collision only. This is for electronic inside only. And this is a combination of the two, which is clearly the sum of the two. So we are another time in this regime around 5 MeV, a combination of the two electronic and nuclear stopping power. So in this regime, we have to be careful about the combination of the two, but in another way, this helps us to understand if there is some interactions between the two and to confirm one idea about by the other. So this is the conclusion. Now, if I go to high charge ions, this is a bit more complicated to go on this. And just, I encourage you to see the paper of Dufour. And I just want to go to the conclusions, which is something which is interesting because it shows you what is a part of a deposit potential energy which is given and in which depth which is deposited depending on the beam energy. If you of a potential energy, if you have here, you have different things. Here, the fractions of the beam energy depending on the potential is around 0.5 to 0.6 total, and the depth in which it is 2 nanometers. And this is so small in depth that the nuclear collision will not affect this phenomena. It's a complicated phenomena, but this is interesting because we arrive to something which is cooperative or additive, it is a problem. But by that, we were able to see, to have another time that the maximum depth as a function for different characteristic of a material is something also following a bit the band gap, and there is some material which is out. So there is some open questions in potential atom energy. General conclusions: interaction may appear whatever the objections. In sputtering, which is in annealing of defect, in sputtering for metallic system, the U curve in amorphous SiO2. In crystalline SiO2, we have a cooperative additive which is nearly constant, the cross-section, and why this is increasing, this is decreasing. So there is a combination of the two, certainly. A synergetic effect in titanium. If you add the two, you cannot have these evolutions, but if you combine the two, we have something which is in agreement. And this is an acknowledgement to all the people with whom I have done this work on interactions, which is for me just a hint to say that we could have interaction between the two. And I want to thank you for your attentions by just some picture from the conquest of England by the French people in the year 1000. Thank you very much. So,
there's one more question in the chat box.
okay.
Yeah, it reads, could comparing carbon therapy to proton therapy give an idea what happens to the shock wave?
We have to calculate what could be the increase of temperature by protons. I think that you could have a shock wave which is less efficient, but I have to make calculation with protons. I never make calculation with protons to see what is the pressure which is induced in. Because the pressure can be calculated immediately by proton thermal spike. So we can calculate this very quickly. I think it should not be, you should have a little difference, but not too much. Sorry.
Participants can ask some questions.
Yeah, go ahead. Go ahead.
I could see Sumit Mukherjee, so maybe you can talk to him.
Sorry.
Sumit Mukherjee and Tiso. Sumit,
Sorry,
you have some questions?
Hello.
Hello.
Yeah, can I ask something?
Yes, you can ask something. Go ahead.
Yeah, Master, just for my information, is there any progress on this thermoelastic model?
Thermoelastic, what you call thermal, the elastic collision spike or the word shock wave?
No, this is basically, one can say the shock wave, but actually it is not the shock wave. It is basically the stress effect followed by the spike processes.
Could you repeat your question? I have some difficulty to understand. Sorry.
I'm basically telling that the thermal spike process is there. It is followed by the stress processes.
Yes.
So is there any, the further progress in this direction?
No, till now, no calculation has been done. No. Not, let us say, very, very precise calculations. No. We know that it does exist. We know that does exist. We have pressure inside the track. We can change the magnetic field orientations, but there is no more development till now.
Okay, thank you.
Sir, I'm Indra here. Can I ask one query?
Go ahead.
Sir, you said that you are measuring the track, experimentalists are measuring the tracks using the force microscopy, scanning force microscopy.
Yes.
So mostly what happens there, the tip convolution effects comes into play, and mostly your sizes or track diameter looks bigger than the actual one. So in simulation, how do you consider to deconvolute that?
But in order to deconvolute that, you need to know what is the size of the tip.
Mostly nowadays the size of the tip is coming 5 nanometer radius of curvature, but you are talking about 3.5, 2.6.
Yes, because are you sure that your tip size is always the same than 5 nanometer? Do you have asked to the people who send you the tips? Does they give you an error on the tip?
So these are the best available tips right now, but we are using a 10 nanometer radius of curvature here in IUAC.
No, I know. The problem is the following. I have this question due to my former formations. When I was in nuclear physics, at the beginning we get sodium iodide, which is a very resolution of 10%, or 25%. And then we go to germanium lithium, we arrive to 3% resolutions. So we increase the size of the gamma ray, the determination of the energy of gamma ray by 3%. So I try to take that into account in order to extract the real value of the track size. So this is a combination of the square of the tip size and you have the adding the result, the radius result in square is equal to the radius of a tip square plus the radius of a real object square.
So theoretically you calculate and then you put it, or it is other way around.
I try, no, but I have to go. Sorry, I have to go back to the other.
Probably I understand that using simulations, you are actually calculating the track diameter and you are trying experimentally to achieve that. Whether what should be subtracted so that you get exactly that track diameter experimentally.
But I have to go at the beginning. Sorry. This is here.
Yes.
This is a tip. This is a tip. This is a hillock. And if you put that, you get that. And what we have done is the following, and surprisingly, the height versus the diameter of each, we combine the height and the diameter of each hillock. And we arrive for a specific irradiation, something which is like this. And by extrapolations to a height equals 0, we get the diameter of the tip. And then, with the diameter of the tip, we have been able to extract the radius of the mean radius of the hillock.
Okay. Okay, thank you, sir.
There's no other questions coming up, I think.
So this one in chat box is taken care. Would comparing carbon therapy to proton therapy give an idea?
Yeah, it is taken care. Okay. Yes. Given the answer.
Now we have to make calculation ferment regarding irradiation of water. I just see some track size in water, and we can extract now the value of the electron from the coupling. It was not extracted previously. We get a value, so we can have some better definitions of the temperature and consequently definition of the shock wave, of the pressure which is induced in that. And then after, we have to calculate the shock wave. But I am ready to make some calculations for people who want to do later on some pressure pulse calculation. But we need to know, perhaps with fireman, what is the effect of a pressure pulse on the body. Because firemen know that they have to be very careful.
So any other questions or queries, students or experts here would like to ask? So if not, let us thank Professor Marshall Pureman.
Can I ask a question perhaps to one of you? I don't know. I don't remember when I was the last time in USA, there was one questions regarding the ELOC height as a function of the of the energy, from very low energy to larger energy. And you arrived to a situation when we were not, I don't know who have done that, we were not able to understand the evolutions of the ELOC height as a function of the beam energy. Does somebody remember that or not?
Actually, some student might have asked, but many people have submitted their thesis and also.
What was that? I don't fully get it. What was that point?
Sir, ELOC height versus energy.
At low energy, the height of ELOC versus beam energy.
So somebody had asked this. I am not.
I was thinking about that because when you increase the energy, when you increase the energy, you were decreasing the nuclear stopping power, but you were increasing the height. So there was a contradiction. And my feeling was to say that it is a range.
Range, yes.
Because increasing the energy, you don't remember. Okay, no, but I was just asking that to all students were there, and perhaps this girl could remember this question that she asked me, but perhaps she's not there. That's it.
Okay.
Okay. So, thanking Professor Marshall Pureman.
Thank you very much for your. I expect that it was useful for you. And if somebody wants to have the new copy of my presentation, they can ask me. And I must say to you that there is a version of a thermal spike which is under constructions to be used under window.
Oh, great.
So when it will be ready, I will give you information.
Okay, that will be good.
But formally, you can thank him.
Yeah. So then, if there are no more questions, we would like to thank Professor Marshall Pureman. As you must have all seen, he is besides being a good researcher, he is also a good teacher. So I hope all of you have enjoyed it. As he mentioned, whoever wants the copy of the presentation can write to him, get this PDF of the lecture, and whatever questions you have otherwise. As you will see, most of us have been benefiting with interaction from him. He is always very helpful. So anybody who has any queries or questions can also write to him an email, and I am sure he will be happy to respond to that. So with this, I will again thank Marcel.
So I just want to thank that you invite me to present this to talk, despite the fact that I am not in your world. I'm very disappointed, but that's a life. But that's it. And I wish success for all of you in the future.
Thank you.
Thank you.
So,
okay, sir.
So Ashok, any announcement?
No, maybe tomorrow 9:30 is the session, so 9:20 people can log in.
So students can log in again tomorrow at 9:20, and we will start at 9:30. In the morning session, there are talks by Rahul Singhal and Dr. T. Som, and after lunch we will have again from Professor Hans Hofstadter. He will again give 2 lectures with a break, So looking forward to all of you joining this. And in between, if you have any questions and queries, you can write to Dr. Ashokan, Dr. Indra, or to me, and we'll try to respond to it. So thank you. Unless Ashokan has anything to add, we can close it.
It's okay. I think we can
Say
close
hello
it.
to everybody in
Yes.
India.
Okay, sir. Goodbye.
Bye-bye.
Bye.
If any of the scholars has any point they want to raise, we can have a short interaction. If anybody has any point to raise or anything, general any issue or anything.
Does Som is still there or not?
Som.
Som is still there. I see him. Som.
Hi, Marcel.
Hello, Som. How are you?
Yeah,
I am there. Thank you so much.
Sunit also is there.
Thank you,
I
Marcel.
just want to say hello to you.
Yeah, it was always, as always, so wonderful to listen to you. I mean, I was just mesmerized. Absolutely.
Thank you.
So your
Okay.
health is fine, Marcel. Nice to see you actually after many, many years.
Yes.
Yeah, your health is fine. Take care.
Thank you.
And
I will take care.
Yeah. If time permits, sometimes we'll speak again. Yeah.
Okay.
Yeah.
Don't worry. You can find me by Skype, whatever it is. You send me a mail and we can discuss. Okay.
That's so nice. That's all right. Take care, Marcel.
Take care.
Our best regards to you and your family. Okay.
Thank you very much. The same
You're
for your
welcome.
family.
Yeah. Thanks.
So,
Okay, so we close it now.
okay, we close it. Bye-bye
Okay.
to everybody.
Bye. Yes. Thank you.
Bye.
Bye.
Bye, Ambuj. Bye, also.
Bye.
Bye.
Wonderful organization. Okay.
Thank you. Welcome.
Hi, Foreign. Very nice to see you all, Indra. Very nicely organized. Thank you all.
Okay.